Yeah, good morning or afternoon, everyone, depending on your respective location. It's going to be a good program. We're going to get right into it. Jerry, thanks for the introduction, and I think I'll take it from here. Okay, so just real quick background on myself. I'm a mechanical engineer by degree. I went to the University of Pennsylvania. Uh, After graduation, I'm a Texan. So a Texan with an engineering degree, you end up working in the oil field. So I did contract engineering, contract management, instrumentation, control systems engineering um, before I got into solar. uh, what's interesting about my background with respect to designing solar arrays is that the company I worked for in the oil fields, Fluor, was also building silicon refineries. And they mentioned in a 2005 marketing report on solar, they were building these silicon refineries for the first time. And some marketing guy said, we don't know if this is actually that great of an idea because solar is so simple to design and install compared to a regular power plant that as a business that designs and sells power plants, by scaling up the solar industry, we could be putting ourselves out of a job down the road. And I thought to myself, well, I'd rather be ahead of that trend rather than behind it. So I got into solar in 2008, worked in solar for 12 years. And this program is a fast paced introduction to solar that also puts you behind the desk of a solar designer so that you can understand the workflow process that a project goes through from preliminary design all the way through to project permitting. So we're going to start out with some lecture, and then we're going to get into computer design examples. Let's start out with how to estimate the performance of a solar array. PV Watts is a free software put out by the Department of Energy through National Renewable Energy Labs. It's a very simple interface. Underneath is very powerful solar performance estimating software. This is the same data set that some of the commercial software that we're looking inside of later on in the program. It's the same data set that they pull from when modeling paid for commercial software. That same data set is used by PV Watts. So it's a free resource, and kind of the first thing I recommend anyone who wants to get into solar do is go online to PV Watts and run through an example. PV Watts connects you to the weather data that is connected from local weather stations, whether they be military bases or airports. Those civic institutions have had weather monitoring going back decades. What PV Watts does is it takes the most typical weather month for that month going back decades and says, okay, this is what the weather is typically like here, and I'm going to build my performance data off of the typical weather data. What that means is there is some variation to PV Watts. Hurricanes, blizzards, droughts, all of that will impact your solar performance. PV Watts gives you a conservative, consistent running average of system performance. What I recommend you do when you approach PV Watts for the very first time is input a 1 kilowatt solar array. Now, most solar arrays are much larger than 1 kilowatt, but if you input 1 kilowatt, it results in a scalar. So if you have a 10 kilowatt solar array, a 1 kilowatt array, will produce 90% less. If you know what a 1 kilowatt array will do, you have an 8 kilowatt array, you can just multiply that number by 8, and that's what an 8 kilowatt array will do. And so what I think you should do as the first thing you learn about solar is do a 1 kilowatt solar array in PV Watts and learn what the production of that is in your area. And there's other factors that go into PV watts that you can learn about. They got little information buttons you can click on to learn more about what goes into these particular items. I'm giving you the abridged version. When you get through PV watts, you get a month by month energy printout. So every single month, you know how much energy the solar array produces, as well as a total at the end of the year. I don't worry about the other stuff so much. It's not that that other stuff isn't useful, but that's not what I use PV watts for. I'm going for these production figures. Um, Well, one factor that goes into solar design is roof tilt, and that's an input on the PV watt screen. We see it right here. So what goes into roof tilt? Well, there's standard pitches to the roof, and if you go into the PV watts documentation, you can see what they are. So the default value of PV watts is 20 degrees. That's around a 512 roof tilt. And if you wanted to make it a little more accurate, you could go and put in the actual tilt angle of your roof. The real question is how much does tilt angle really impact solar design? And the answer is not as much as you think. So I've put together this chart that compares a couple of different tilt angles, a 512 tilt and a 1212 tilt. So if you're in Houston, Texas, a due south array at a 512 tilt, which is about 22 degrees, produces this much energy. And if you go up to a 45-degree tilt angle, so from 22 to 45 degrees, that's over a 20-degree difference in tilt. You lose about 5% of your production. That's not terrible. Am I going to take a roof surface and artificially install a racking system to tilt the panels up off of the roof by 20 degrees in order to gain 5% additional production? Probably not. Even if the cost to do that were less than 5% of the project cost, you get into structural issues and shading issues when you tilt the module up off the roof surface. So no matter where you are, in almost all circumstances, you are going to follow the tilt of the roof with your solar array. You're not going to, if it's a flat roof, they do give it a little bit of a tilt, but they don't tilt it all the way up to some theoretical magic tilt angle that gives them the most amount of performance. Back in the day, like in the 70s, you would do that when solar was very expensive. You would be very concerned about how to get the most amount of power out of a solar panel. Now we take a more pragmatic approach to say, well, is it better to, or what, if we deviate from ideal, are there any advantages to do that? And what we can see is just the tilt angle. The performance does not matter that much. What about going from a south orientation to a southeast orientation or a southwest orientation? So how you orient on the compass, the way the solar array faces, does that make a lot of difference? And the answer is it makes even less difference. Like if you go from a 512 tilt angle due south to a 512 tilt angle facing southeast or southwest, you only lose 3% of your production. And so, that's not a substantial amount of loss. And in fact, the shallower your tilt goes so that your modules are facing straight up in the air, you're only losing 7% of your production in Houston, Texas, as compared to a 512, kind of more of an ideal roof surface. So even going straight up in the air isn't the worst thing in the world. We don't do that for other reasons. The rainwater, you want it to drain off of the solar panels. So even on a flat roof, typically you're giving the module some tilt for rainwater runoff. but you're only losing 7%. And if a module's facing straight up in the air, whether or not it faces east or west or south, which, that doesn't matter. The panel's facing straight up in the air. And what that means is the shallower the tilt angle of the solar panel, if it's at a shallower angle, then the orientation, whether or not it faces southeast or southwest, it matters less because it's approaching a flat panel that faces straight up in the air where orientation doesn't matter. And so that might be a complicated way of saying whether or not the array faces due south or southeast or southwest has very little impact on the actual performance of the array. So there's a lot more flexibility in how you point the solar modules than you might think. So even going in a southern latitude like Houston, Texas, even going from due south at a variety of tilt angles all the way to due east or due west at those same tilt angles, you're only losing 3 to 7% of your production going all the way to due east or all the way to due west, as long as you're at that shallow tilt. Now, at a steeper tilt, at a 12-12 tilt, the impact of the orientation of the array is greater. We lose 20%. So maybe at a steeper tilt angle, the orientation of the array begins to matter more, but still we're only talking about a 20% performance loss, not something like it won't work if it's not directly facing the sun. On top of that, sometimes, if the choice is between a south-facing roof surface or twice the surface area facing due east and due west, sometimes doubling the project size can reduce the cost of the project by more than 20%. And so there's a number of circumstances where an east-west array can be more economic than a smaller south-facing array. For that matter, the orientation of a north-facing array at shallow tilt angles is also not the worst thing in the world. If you have a terrible roof for solar that faces south, and a really, unshaded roof that faces north at a very shallow tilt, that north-facing roof surface might still be eligible for, areas where solar is already valuable to begin with. Of course, when you go to a steeper tilt angle, the impacts of the orientation matter even more. But look, even on the north side of the roof, at a 45-degree tilt angle, facing where the sun isn't, facing the north part of the sky. In Houston, Texas, a north-facing array at a 45-degree tilt angle will produce half as what a solar array at that same steep tilt angle does facing south. So it's even in extreme circumstances, it's not like the solar panels won't work. It'll just be difficult to make them economic. Now, the further you go north, not Houston, Texas, but Indianapolis, what we see is the trends are pretty much the same. Going from a due south orientation to a southeast or southwest orientation at a steep roof tilt, we're only losing 6% going from due south to southeast or southwest. We lose about 15% going at a shallow tilt angle to due east or due west, and we lose about 23% at a steep angle facing due east or due west. So if you're all the way up in the north part of the United States, a due east or due west array at a shallow tilt angle is probably acceptable, but you have to be a little bit careful the steeper your roof gets. Similarly, the further north you get, the less valuable that north side of the roof becomes. But there still are enough special cases to, I say, evaluate any good open roof surface for solar with the understanding that southern oriented roof surfaces are the best ones to go after. But here's an example of an extreme case. This is popular in New York City. It's called vertical solar, where they put the solar array down the side of the building rather than up on the top. If your building is tall and skinny, you might not have space on your roof for a solar array. But in New York City, the cost of electricity is so expensive that even an off ideal solar array can make financial sense. And so they, a solar array that hangs down the side of the building, in New York City produces only 30% less than what a typical commercial rooftop system up on the top of the roof would produce. But you have all that extra surface area. So, is this an impact statement? Yes. Is it more expensive to install a solar array down the side of the building than on top of the roof? Yes. But at the same time, there are market applications of vertical solar that are pretty interesting. If you're doing off-grid design, if you're not doing a big expensive commercial project, but you're trying to power a hunting cabin in off the Great Lakes, maybe you hang the solar panel down the side of the building to not accumulate as much snow, because you're trying to get that electricity at super critical times of the winter. So the cost of solar has come down to the point where we can be a little bit more creative and flexible in our design than what the market was like back in the 70s, 80s, 90s, and even early 2000s. So long story short, you do a PV watts example, say for Houston, Texas, and you find that 1 kilowatt of solar produces between 1,300 and 1,400 kilowatt hours per year, which is pretty typical for most of the United States. In the sunny desert in the Southwest, these numbers will be maybe 20% higher. You get up into North Alaska, these numbers might be 25% lower. But for most of the United States, in Wisconsin, and in Texas, in Pennsylvania, 1 kilowatt of solar will produce between 1,300 and 1,400 kilowatt hours per year, assuming it doesn't have shade. And what I do with that number is divide by 1,000. I say, okay, a lot of stuff in the solar industry is broken out by the watt in the solar industry. And so 1 kilowatt divide by 1,000, you get to 1 watt. 1,300 to 1,400 kilowatt hours divide by 1,000, you get to 1.3 to 1.4. And I memorize this number and use it in so many solar conversations, because if someone comes to me and they say, hey, I'm using 13,000 kilowatt hours of electricity a year, what size solar array do I need to offset 100% of my energy use? They might say it a little differently than that, but if they're using 13,000 kilowatt hours of solar a year, and I know 1 watt produces 1.3 kilowatt hours per year, then they need a 10,000 watt or a 10 kilowatt solar array to generate as much electricity as what's used by their house, which is a standard residential configuration. Not quite the end of the story, but right now, if you go and do a PV watts calculation in your area, and you know what 1 kilowatt will do, so you know what 1 watt will do, you memorize this number. 1 watt produces 1.3 to 1.4 kilowatt hours per year, and you understand that whether it's a south-facing array or a southeast-facing array or a southwest-facing array, or maybe you have to discount this number by 10% if you go to, or 15% if you're going east and west. But for most circumstances and most roof tilts, this number is going to hold true. That means you can have in conversation just general estimate conversation about solar array size and performance. If you know it's a 8 kilowatt solar array, and you know 1 watt produces 1.3 kilowatt hours per year, you know, 8 times 1.3, you know, that solar array is producing about 10,500 kilowatt hours per year, more or less, give or take. Now, that's not the end of PV watts. It's not that simple. PV watts, in addition to giving you this annual number at the end of the year and the monthly report and the annual report, that's where most people stop with PV watts. But what's great about PV watts is if you take this, if you're on this final screen for PV watts and you scroll all the way down to the bottom, you get to this hourly export. And in this hourly export, you get to download all of the data that PV Watts is using to crunch the numbers behind the scenes. And so you can get information like how much sunlight is in the air, how much of that sunlight is being diffused by the clouds, what the temperature is outside, how much sunlight is actually, you know, coming in from the air and hitting the surface of the solar panel, what the temperature of the solar panel, that rooftop temperature, actually is, and then finally what the system is going to output after all the degradation factors that PV Watts considers are taken into account, which are your standard degradation factors for an unshaded solar array. If you're modeling an unshaded solar array, you don't need to make many changes other than the direction the array faces and the system size in order to get a very good conservative estimate out of PV Watts. But you can fine tune a few numbers. It takes longer than a 4-hour class to really get into everything that we're trying to cover, plus all these technical details. But the point of it is PV Watts, because it'll tell you how much sunlight is in the air, how much sunlight's being diffused by clouds, it will tell you how many cloudy days in a row you can expect over the course of a given year if you analyze the data. That's great information for planning off-grid design and also some commercial battery storage design as well. So in addition to sunny days, it tells you cloudy days. If you want to know how hot it gets up on the rooftop, in addition to ambient temperature, it tells you rooftop temperature, module temperature. Some of the other stuff like wind speed really isn't that important, but at the end of the day, you're getting an hour by hour printout of every production figure that the solar array will go through throughout the calendar year. And that hourly printout is useful if you have time variable rate structures, peak and off-peak rate structures for additional analysis. You know, when I'm building my models, if I'm doing a solar model, you know, using the pencil and paper way, or even just doing some preliminary planning, I'm always taking this hourly data and then exporting it, throwing it into a spreadsheet, and starting to analyze the numbers as a good starting point. So just some additional examples. Here we have beam irradiance, which is the amount of sunlight in the air. And on January 1st, you know, the sun's coming up in the morning and it's setting in the evening, and we see this steady rise and fall of sunlight in the air throughout the day. Well, then on January 9th, we don't have any numbers. We have a little bit of sunlight right in the middle of the day, but otherwise the sun's gone. Now, what happened then? Well, you know, it's not that the sun's gone, it's that we have clouds, we have diffuse irradiance. And so on the sunny day, we had very low diffuse irradiance numbers, and then on the cloudy day, we see an increase in diffuse irradiance and a decrease in direct irradiance, and that translates into lower production figures from the solar array. And we also get to see our maximum production figures. On this sunny day in the wintertime, our 1,000 watt solar array is only getting up to 600 watts of power. You know, a solar array rarely generates its nameplate capacity. The nameplate capacity comes from a laboratory standardized test similar to the mile per gallon rating on your automobile. You know, it's not really indicative of field performance. It's more like a performance benchmark to assist labeling and comparison. But here in the wintertime, this 1 kilowatt array is only getting up to 660 watts. You know, back in the day when the rest of the system was also expensive, we would analyze these figures to much more scrutiny when it came time to select our materials so that we wouldn't waste our budget. It's called right sizing. You know, as material costs come down, the need to right size certain aspects of the project becomes less important. All right, well, let's talk about very quickly what goes into those PV watts degradation numbers. You got a 2% allowance for some dust on the solar array. And all I have to say about dust is that if you live on a dusty road, you're going to get more dust on your array. If you live right by a pine tree forest, you're going to get a lot of pollen on your array. And so, in those circumstances, maybe it's a good idea to do a ground mount instead of a roof mount if you can, just to make cleaning the solar array easier. But in most circumstances, a solar installer is going to tell you that you do not need to clean your solar array. And what they're really saying is, hey, buddy, the rooftop's a dangerous place. If you go and scrub your solar array, you might see a 2% increase in the performance of the system, but is that really worth getting up on the rooftop as a chore? Probably not. So it's a good idea to clean the arrays, but I would wait for other system maintenance events. You know, if there's something going on with your array and it's the array's been sitting there 4 or 5 years untouched, rather than have the guy come out and paying him just to do some diagnostics, maybe that's a good time to kick the solar installer, you know, some money to go out and clean the array while he's also out on site doing other things. You know, it's not a cleaning the array is not a regular task. They put surface treatment on the solar modules to have it repel dust. You know, solar panels can tolerate some dust. They can't tolerate the Sahara Desert covering them up with sand. There's a little bit of an allowance in PV watts for dust. PV watts really does not allow for shade. This 3% number is really saying that PV watts is telling you every kilowatt hour as soon as the sun rises in the sky, but your inverter components may have a minimum power requirement to operate. And so PV watts is taking out 3% of the amount of sunlight that it could be producing through the system and saying this is going to apply to early morning and early evening low light conditions where the system isn't turning on. So PV watts really does not evaluate shade like a commercial software does, and we're going to talk about that later, so we're going to keep going. PV watts does not evaluate snow. And so if you live in an area where there's heavy snow every year on the rooftop, the solar array may not be very productive during those times. How productive will it be during those times? Well, it does depend on the snow, but we can start to take some guesses at that because we could look at a sunny day in PV watts versus a day that's completely overcast, and we see that the solar array is producing, about 15% of what it would be doing under full sun. So if there's snow on top of the array and it's only a thin layer of snow, still your production is going to drop by 80% until that snow is cleared. Now the good news, and again PV Watts can tell us this. Let's see. I thought I had, there we go. Yeah, so the good news is your wintertime months do not produce as much as your summertime months. So losing to this is Houston, Texas. So it gets even gloomier in the wintertime the further north you go. Like if you go to Buffalo, New York, you're not going to get tons of summer of wintertime output to begin with, and losing a couple of weeks of production in the middle of winter from a pure economic standpoint is better than losing a couple of weeks of production, at more productive times. So, wintertime snowfall, while it's not great, it's not the end of the world either. Some of this other stuff has gone away. Module mismatch. Nowadays, we're using more expensive electronics that gets rid of this entirely. So PV Watts is a little conservative on that end. Um, Voltage drop is generally sized around 2%, although it can be less than that, maybe 1% at a minimum. Then there's some degradation figures that we're not really going to talk about in great detail. A light induced degradation is kind of the solar panel losing its new car smell, where the electrons, when they're going through the motions for the very first time, they have it's like an ice skater on an ice rink. That's just been, is it Zambonied, where the ice skating rink is perfectly smooth and the electrons can go wherever they want. All of a sudden, these electrons start etching pathways into the silicon, and like a bowling ball going into the gutter in a bowling alley, that electron, when it goes into a pathway of a previous electron, it loses a little bit of momentum as it falls into that pathway. And so in the first couple of months of system production, your solar array is going to lose about 1% of its sticker capacity because of light induced degradation. Age will similarly degrade a solar panel. Um, the thermal expansion on the panel every single day in a hot, a humid environment will work impurities into the build quality of the solar module. So it is a weatherproof device, but the top is more weatherproof than the underside. The underside is still exposed. Nature is a very powerful thing when you give it a long period of time. PV Watts is not accounting for degradation caused by age, but it's about 0.5% a year. Finally, we get to system availability. This is where PV Watts is again being too conservative, in my opinion. It's assuming the system is going to be offline for 3% of the year, which is about 9 days a year. And if your system is offline for 9 days a year, um, if it's a regular batteryless, simple solar array, then you probably picked the wrong installer. There's probably something else going on aside from the components themselves that is causing you to have such low usability. So overall, PV Watts errs on the side of being conservative. If you don't change this number, this 14% loss factor for an unshaded array, then you will be underselling your customer and over delivering, which is a little bit better of a situation to be in than the other way around. So, just use, especially when you're first getting started in the industry, use the PV Watts standard degradation factor, and you'll be just fine. Again, PV Watts, while it's not modeling snow, it is modeling the system being offline for 9 days out of the month. And so, that gives you a lot of kind of gray area or wiggle room in most circumstances. Okay, so let's talk about some system economics. The price of electricity changes, and you have to know the value of the electricity that you're getting out of the solar array. And that can be a very complicated calculation, or it could be a very easy calculation depending on what your policy is, what your utility policy is. But at any rate, once you determine your effective value of your electricity, if a peak and an off-peak rate might have two different values that you have to do a weighted average and smush together. But once you know the effective generation rate of the solar array, um, then, and hold on one second. Hey, Susan, can you turn that off? All right. Um, Once you know the effective generation rate of your system, and you know that 1 watt of solar will produce 1.3 1.4 kilowatt hours per watt per year. Remember, we got that number from PV watts. That's a number that most solar installers don't use, but I find it incredibly useful. But if I know what my effective generation rate is per kilowatt hour, and I know how many kilowatt hours per watt per year my solar array is going to produce, well, then I know how many dollars per watt per year my array is going to pay back. And a lot of solar installation price is done in terms of dollars per watt. And so if I'm saving at 14 cents per watt per year and I want a 10-year payback, which I would say most customers want, that's not easily achieved, but I'd say this is what, when a customer says, I want to buy solar, and then you say, well, how many years will it be satisfactory to you to get your money back? Someone will say, oh, I want my money back in a year. So, well, if that were true, then we would be 100% solar powered by now, because everyone would be going out and doing it, and that's not happening yet. We're not at a 1-year payback. Many customers want 5 or 6 year paybacks, and maybe in some regions subsidy programs can get you there. But if I wasn't receiving any kind of subsidy for solar, and my solar array is saving me 14 cents per watt per year, and I wanted a 10-year payback, I would need to have $1.40 per watt as my installation price. Now, in the United States, we like to complicate things. We do provide tax credits for solar power, and I'm hesitant to call them solar tax credits because they're part of larger energy bills, and believe me, the fossil fuel industry gets their fair share of those larger, broader energy bills. So, just to single out the solar tax credit by itself, might be disingenuous. And solar pays its own taxes too. We have very steep import tariffs that, to a large extent, offset the tax credit gain. So our solar costs in the US are artificially high, and then we also artificially lower them through the tax credit. And none of that eventually makes a lot of sense, but really that's for another time and place, a different kind of discussion. In the United States, we do have a tax credit on total system cost. And it's actually no longer 30%. It's beginning to step down. So right now, it's at 26%. Really not that different than 30%. It's at 26% this year. It's at 26% next year. The year after that, it's supposed to drop down to 22%. So next year is a really good year for solar power. And then the 22% is supposed to stick around for 2 or 3 years, and then it's going to drop down to 10%. So this upfront tax credit is currently fading out. And, to be quite honest, if it fades out in the same schedule as the import tariffs, then, we could probably get down to $1.40 a watt, um, 5 or 6 years from now. We're not there yet. And so what you would do instead is take that value of the tax credit. In this equation, it's a 30% tax credit. But if we would have to adjust it to 74%. And so then we divide, if we want a 10-year payback and we're saving at 14 cents per watt per year, and then you divide by the value of the tax credit, basically under a 30% tax credit rate. What I'm trying to say here is for most of the United States that is producing an average amount of solar production with an average electricity pricing, with the tax credit and very few other incentives, you would have to have a $2 per watt installation budget for the project to have a 10-year payback. Now, some customers are fine with a 12-year payback. Some are even fine with 13 or 14. You get much beyond that, you start selling more solar as a toy rather than as a money saver. Now, the national price for solar is around $3 per watt. And so the question becomes, well, are all these customers buying solar for economic reasons because they're really going to be getting 15 or 16-year paybacks even with the tax credit? Well, the answer is, well, sure, there's some, not every aspect of the solar industry is rosy. There's some sales reps out there, there's some solar companies out there that really push the cost savings of solar, that in certain locations you get things wrong, those cost savings may not fully materialize. But what I would say is, does solar have to be installed at $3 a watt? Can it be installed more cheaply? And then also, are there areas that can command a $3 a watt price and still be cost effective? When we talk about solar, it's very easy to get wrapped up in the production value. How much does solar produce in the desert versus how much does solar produce in the Northeast? I think we have some attendees from Wisconsin, and Wisconsin actually gets better sunlight than most of the Northeast. It's kind of right on that edge. You actually get about the same production in Wisconsin as you do in Texas, because it's not just sunlight, it's also humidity and temperature and other factors. But at a basic level, you take a solar array in Phoenix, Arizona, and you compare it to upstate New York, and the production value is going to change by 50%. And from outside of those extremes, it's a much closer together figure. You take the same extreme and you compare, the price of electricity in Albuquerque, New Mexico. You compare the price of electricity in Albuquerque to the price of electricity in New York City, and the price of electricity in New York City costs 3 to 4 times as much as it does in Albuquerque, New Mexico. So the performance varies by 50%. The value of the electricity varies by 100% or more. And the value of solar is the multiplication of the two. It's how much sunlight you produce and what that electricity is worth. And because the price of electricity varies more than the amount of sunlight throughout the country, the solar market is driven by electricity pricing and not by sunlight as its primary motivator. Yes, there are certain markets like California where they get both high price electricity and really good sunlight. And of course, that is going to be a great solar market. But the Northeast coast is also a very good solar market, even though they don't get good sunlight because of the price of electricity. And the more detailed you get in this industry, the more you can start designing systems to go after a customer's specific rate structure. And especially with the variable rate structures that you have today, you can find variable rate structures that are very bad for solar and variable rate structures that are very good for solar. And so the question is, how do we make solar more cost effective, particularly in the middle of the country that has low cost electricity and average sunlight? And the answer is, don't race to the bottom by trying to sell the cheapest solar array possible, although in certain markets, that's the only market. But instead, be a little bit smarter and start looking up the electric rates of your actual clients to say, hey, I noticed this has a pretty extreme variable rate structure. Maybe a little bit of on-site energy can be cost effective in that manner. So we're going to talk about some of that in greater detail throughout class, so no sense in spending more time on it now. Now, is it possible to lower the price of solar through good project management? The answer is yes, particularly at the residential level. My common recommendation is to divide the design work from the labor. If you have the plans already drawn up, if you have the materials all ready to install, and you can just go to the installer to say, give this to your permit office, send your crew out, put it on my rooftop, you're taking on more project management roles and you're making the installer's job a lot easier. So some energy, buildings, you have the architect design the building and then the contractor build the building. Solar is done much more frequently under a turnkey specialty contractor development schedule. And I think this is where engineers in particular fit into the industry really well to say, well, how do we plan the projects so that we don't need, a high price specialty contractor on board, but let's bring on, a mainstream electrician. And if you can divide up the scope that way, that is one way to lower the price. Now, that's not to say you don't get value with more expensive things. Sometimes you do, sometimes you don't. But let's take a look at these schedules, these budgets. The big turquoise color here is called soft cost, and that is supply chain markup, overhead like insurance costs and things like that, and then profit margin. And in utility scale projects and even commercial projects, that soft cost is a much smaller portion of the project. The larger the project gets, the less of the project costs are things like the design, engineering, and permitting, the soft costs. Even the labor budgets go down as the larger the projects get. Actually, the cost of the solar panel itself doesn't change very much. So one way to lower your cost is to put the material out kind of in a competitive bid situation for the material. That way you can reduce a portion of the soft cost for free. Maybe by procuring the material and design work on your own, you're eliminating, some of the roles and responsibilities of the installer, and so you do get that project cost down, to the point where you can get a 10 or 11-year payback. Now, back in the day, and still in some spot regions, the solar installer is a subsidy expert. And so he's, jacking his price up to optimize the value of the subsidy. And maybe in turn, he's selling you, higher end, top shelf products. It doesn't necessarily need to be that expensive. So kind of the key takeaway here is to get multiple bids regardless of how much involvement you actually want to have in your project. Multiple bids is always a good thing. It's not so much that the cheaper installer is better. It's just that, by letting all the contractors on the project know that you are getting multiple bids from multiple companies, as if by magic, that project budget starts to dwindle. And then finally, if you're willing to roll up your sleeves and take on some of the job scope yourself in terms of front-end project planning, that's another great way to lower these soft costs as well. Now, I think what's another thing that's really interesting is the commercial solar market, because they have the economies of scale and the lower budgets similar to utility scale, except commercial projects are still consumers. They're still behind the meter rather than in front of the meter. They're still the people who buy electricity and not the people who sell electricity. So utility scale plants, they need these economies of scale to be cheap because they still have to mark up the electricity and sell it at a profit. Whereas the consumer, on the other side of the meter, the consumer, theoretically, they can save at retail price because they're buying at retail price. Now, it's not that simple, but what is neat about commercial solar in particular is you get the economies of scale of larger projects, but you get the retail savings of smaller projects. So the commercial market should be just booming, yet it's not. So it's mysterious. The commercial solar market should be great for solar. It's the smallest market segment right now. Why is that? Well, it has to do with the buyback rate. It has to do with what the utility, not just to do with what the utility is buying the electricity for, but also how the electricity is charging the client, the end user, for their electricity. So at the residential level, there are consumer protection laws that make this simple for the consumer. And it's called a net metering policy. And so there's a website you can go to called Desire. It's DSIREUSA.org. It's run by the North Carolina Solar Center. It's a database of all the policies and incentives for all kinds of renewable energy projects throughout the United States. Great resource to use. Net metering deals with buyback rates from the utility for solar that is being outflowed onto the grid. And so in the state of Nevada, they say our net metering policy is only going to apply to investor-owned utilities. So sometimes electric cooperatives are exempted from net metering policies. Occasionally, they voluntarily have them. But what is more likely the case in many states is they might have a state-level net metering policy, but they exempt the electric cooperatives, and then whether or not you have a net metering policy in place may make or break your project. This says net metering applies to commercial, industrial, or residential sectors. Except that's not the whole story, because commercial and industrial customers are billed differently for their electricity. And furthermore, commercial and industrial customers may have on-site energy uses that are so large, whatever size solar array you can fit on the roof might not be enough to sell back to the electric grid. But a residential system, a residential system only produces during the day, and yet a commercial, residential electrical load, sure, it's very little at night, but then it spikes in the morning, and then it continues to rise throughout the day, and then it drops back down at night. And if you want to eliminate the entire electric bill of a residential home, you're going to have a substantial amount of system outflow, way more. If solar only works for a third of the day, but it needs to offset the electric bill of 100% of the home, then 2/3 of the solar array production by necessity will have to be sold back to the utility, and you're only going to be able to offset the bill in a 1-to-1 ratio if the utility agrees to pay you in a 1-to-1 ratio. And by and large, now there's always exceptions to the rules. Mississippi is an exception to the rule. Their net metering policy says we don't have net metering effectively. But in most states, if you have a net metering policy in place, it entitles you to something close to a 1-for-1 exchange of value for what you sell onto the grid and then what you buy back from the grid. The problem is for commercial and industrial is that 1-for-1 exchange only applies to half of their bill, and the other half is calculated completely differently. So net metering is really a residential policy, even if it applies technically to other sectors. And it guarantees the consumer the ability to have a cost-effective solar array, essentially. Now, there's always exceptions. We're going to talk about some later on in the program. So, in interest of time, we're gonna kind of move on from the net metering discussion. But just know that go to the Desire website, DSIRE. Go to the Desire website to find your net metering policy, because they can vary greatly. In Nevada, they limit the solar systems to 25 kilowatts in order to get that near retail rate. And anything larger than that, effectively doesn't have net metering. And in other states, instead of being a 25 kilowatt limit, it might be a 10 kilowatt limit. Or it could be a 5 megawatt limit. There is no federal net metering policy. The federal government historically has not regulated the price of electricity. And net metering would be a step towards regulating the price of electricity. So even though net metering may be, it's not a perfect policy, not everyone likes net metering policy, but as far as green energy policies go, it's probably the least costly green energy policy we have. And it's a very consumer-friendly policy. So in terms of being one of the better energy policies available to us, it's a nice selection, but it's not perfect. It's easy for utility in the long run to manipulate how they buy and sell electricity through their rate structure. So even when you have net metering, down the road, it could be watered down, and it varies from state to state. We're going to talk about some tactics to get out from reliance on net metering. If you have a good net metering policy, the threat of losing it should not prevent you from doing a project. It's more like you want to get it secured now, and because it might not be available in the future. So here's what I think makes a pretty good project budget. It does involve doing some bargain hunting on solar panels, but we're going to talk about what I like in a solar panel, and that's kind of what this budget reflects. Um, I usually spend a little bit more on my inverter system. You can find cheaper inverter systems than this, but the inverter is the heart of the system. It's the system electronic component that does everything. You um, so and then the racking solar rail is racking is pretty cheap. It's not that expensive. Um, Yeah, I think as far as your project overhead soft cost, you could if you're let's say you're doing the array layout and you're providing the modules, the inverter, and the racking, and you just want to hire a solar installer to show up with a crew and supply the balance of system material. I think in most parts of the country, certainly Wisconsin, you can find installers who will show up and do that for a buck 30 a watt. And I think in Wisconsin, in particular, there's a sales tax exemption. About 25% of the country has a sales tax exemption on solar. So that's another thing you can use the Desire website for, and that will just flat out knock 1 year off of your payback if you can get rid of the sales tax exemption. And I think that's a pretty fair policy because a lot of power companies, when they build power plants, they get sales tax exemptions, so that helps level the playing field as well. And so now our economic calculation is a little bit more complicated. We back the sales tax out of our, I think a managed project budget rather than just thrown out to one solar contractor you see. So we get a little bit of a lower budget through competitive bidding. We identify a sales tax exemption. We're still modeling the tax credit here. In Wisconsin, you might have slightly higher electric rate generation rates, about the same production, but of course the tax credit's now worse. So I think right now in most of the United States, a managed solar project with a net metering policy is going to get you about a 13-year payback, including the federal tax credit. Now that is not a good enough payback to get a lot of people to jump out of their seats and go do solar. So we might have to be a little bit smarter about how we're planning our projects, but some people will. And particularly if you put a 13-year payback into a 30-year mortgage, you're going to take more off of the electric bill than what you'll add to the mortgage payment. Now, that's not without risk. Taking a mortgage out on your electricity to put a solar array on your rooftop will only save you a small amount of money, particularly because of the financing cost. The financing cost is many solar installers will not factor that in to their cash flow model. But the short of it is, if you have to have a simple payback that is, about half the loan term or less in order for that device to generate more value than what the interest cost will add back into it. But I think it's still pretty impressive that if you want solar on your home, that you can put it into a 30-year mortgage and and have the solar array pay for itself. Um, there are other reasons to buy solar than just economics. I talked with a customer recently, and he said, I do like the fact that I'm getting my money back, and I wouldn't be doing it if I didn't get my money back, but I do want to leave something there for the kids. And so if I use less fossil fuel for my own house, that will set up, the earth is a better place for future generations. There is that environmental altruism aspect, regardless of your political divide, that motivates customers. And a swimming pool can't do that. A swimming pool can't pay for itself in a way a solar array can. The point is, you need to make sure that if you're financing solar, that you have to be getting a really good deal on the price. I've seen customers just being told that they're getting a good deal and that the loan will save the money by out of state high pressured sales online solar companies, and it results in the customers who take that free money quick pitch. It results in them losing all of the money they have in their bank. And so, you have to really understand financing before you can go out and recommend it. Essentially, if you have a 20-year loan, you need a 10-year simple payback for financing to make sense. If you have a 30-year loan, you need to have a 15-year simple payback for the financing to begin to make sense. And solar is now kind of within that margin. So let's talk about the array layout. And we're gonna take a break at a quarter till. So we have another half an hour of program content. And well, I guess Jerry said he's going to do his roll call, but we're going to take a 30-minute break at a quarter till and go from a quarter till to 15 after. So let's keep plugging along. But we'll have a break coming up in about a half an hour. The solar array layout is a solar array that a rooftop solar installer would love to see. Architects hate it, solar installers love it. A large, open, boring roof surface that you could just cover with solar and capture a lot of sunlight. So large, open, boring roof surfaces. We already considered well, let's expand this discussion we were having earlier about usable roof surfaces. What's interesting, let's say you have a 12-12 roof in Indianapolis, Indiana. Going into a due east or due west at a 12-12 roof, which is not a walkable roof pitch. You really 512 and less is what's walkable. So at a 45-degree angle, pretty steep, you lose 23% by orienting the array from due south to east or west. So if you had a due east and a due west array, your total production is 154%. If you have a due south and a due north array in the same location at that same high roof tilt, your production is 144%. So the east-west array will produce a little bit more than a north-south array. And a south-only array will produce the most per panel, but maybe not the most out of the roof. So, for all of those reasons, it might be that 100% south and doing a small array is the most cost-effective. If there's not a good utility buyback rate, there's no reason to do the larger array. But if there is a good utility buyback rate, then maybe doing a larger array and getting more production out of it is the way to go. And then in that case, might as well keep going and evaluate, every section of the rooftop if you still have budget available and it's still making cost-effective sense to do so. And so I'm not going to go through the calculation. Basically, what I'm saying is if you have the choice between, a complicated, smaller solar array at a higher project budget versus a larger comprehensive project, a much larger solar array, you might be able to get a lower budget. And so you chop down this shade tree and then cover the whole roof. And on this, shallow tilt 512 tilt rooftop in the southern part of the United States, a northeast facing solar array can still result in a more cost effective project than just sticking to your ideal roof surface angles. Let's talk about solar panels for a minute. A typical solar panel is 3 1/3 feet wide by 5 1/3 feet tall, about the size of what one person can pick up in a portrait orientation with their two hands in front of their body, about 3 1/3 feet wide, and they can still see over the top of it, about 5 1/3 feet tall. Weighs about 40 pounds. Residential sized panel is designed for kind of a person to pick up and see over the top. A utility sized panel is just a little bit taller and a little bit heavier. Technically, residential panels are referred to or called 60 cell panels because you can count the cells, and there's like let me remove my scribbling, but there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cells here. On this utility scale panel, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 2 more rows of cells, and that means the utility scale panels are a little bit taller, a little bit heavier, about 50 pounds instead of 40 pounds. So you don't want these 72 cell utility scale solar panels up on a slanted rooftop. They're just too hard to maneuver, and either way, manufacturers know they're rated to work outside. So they're rated for 1-inch hail, 25-year warranties. Now, solar design is how many rectangles can you fit on a larger polygon. It's not that complicated. Sure, there's some finer elements like maybe shifting the array over a couple of inches so that it looks perfectly centered, except noting that the door of the building isn't perfectly on center. And so making a determination of, well, do you center the array? How do you center the array aesthetically? Those are easy, fine elements of solar design that are kind of enjoyable parts of the job. But ultimately, you take your dimensions of your solar panels, you tile them across the rooftop, and then you know your array size and you know your project size. You plug that into PV watts, you know your performance estimate. Really not that big of a deal. And yes, there's some finer design elements to know, but a good rule of thumb is to keep the array accessible and keep the array looking good. And you do these 2 things and you have a good solar design. Anything more ambitious, if the array isn't accessible on the rooftop, then it's going to be difficult for whatever maintenance needs to be done down the road. And if it doesn't look good, then actually what a lot of solar installers don't understand is at the residential level, most of the value that the solar array adds to the building comes from its appearance, not from its production. So the appearance of the system is very important. Let's see. So we did on this design, we chose the south-oriented roof surface first, but then we still had an electric bill and we still had budget. So we did this was in Wisconsin actually. We did a east and west facing array, and then we ran out of budget. And so at that point, even though we had a good north facing roof surface, we stopped because, hey, we're out of budget. That's all we can do. No problem. That's a good project. And if we had even less budget, then getting rid of the east and west facing arrays would have been fine too, and just use the best roof surface. No big deal. Fire code requires access to the roof. So 3 feet off the top of the roof and 3 feet off the sides is your standard residential setback requirements. There are exceptions, but 3 feet off the sides, 3 feet off the top, you really can't go wrong with that. And this is why the firemen on every roof surface need to be able to get up on that roof and cut a hole through the roof to get the smoke out of the building. Not all jurisdictions enforce this aspect of solar design, but it is part of international residential code. And so, and many jurisdictions are aware of it. You don't want to get surprised. Don't push unless you're pointing it out in your review. Keep your solar array 3 feet from the edge so that the firemen can get up on that rooftop and cut their hole. And in fact, if you have the space, 4 feet from the edge is a lot more comfortable than 3 feet to the edge. So I like doing 4 feet to the edge because I don't like my knees to shake when I get up on the rooftop. I like nice, comfortable distances. And then in commercial design, there's setback requirements too. In commercial, it's 6 feet from the edge. And that's a good principle as well because you might design the array to be inside the roof enough so that the crew doesn't need to wear fall protection equipment per OSHA guidelines. So staying 6 feet from the edge can get you out of that. Every 150 feet, you need a walkway. Now that walkway requirement is good for accessibility. It's also good for thermal expansion. There's been some mistakes in solar arrays in years past that didn't allow for thermal expansion of these giant metal structures on top of the rooftop. It resulted in the solar array pulling itself apart and some of the loose metal conduit coming out of its fitting. So even though the fitting could be installed perfectly correct, the thermal expansion, once you get above about 150 feet, becomes strong enough for the fittings to pull themselves apart, and that can result in fires. So fire code has now adopted it. It's just this is not part of National Electric Code, so you need to look up building code for your setback requirements. And of course, sticking to the interior of the rooftop is a good idea to begin with because you get higher wind speeds around the edges and the corners of the rooftop. And so the interior of the roof has less wind speed. And actually, if you get into your racking design, you'll have different tolerances for your racking depending on what zone the array is in. And so the distances between your attachment points on the rooftop can change based on whether or not you're at the corner of the roof or the edges of the rooftop. Solar installers, by and large, are very conservative on their racking attachment spacing. It's standard to do it 4 feet from the edge, 4 feet on center. And so the end result is a nice aesthetic, but there's a couple of finer notes that I want to point out. One is the attachment points that are underneath the array, they don't extend out on the array. You don't see a stick of rail, coming off the edge of this array here. All of the rail is tucked in underneath. And there's some finer racking systems that go a step further. My systems that I use are not high end, and the rail just sticks out, an inch or so and clips on to the last module here. But from a distance, you can't see it. So at any rate, what we do is carefully plan our attachment points so that they are inside the interior of the solar array, and there's a little bit of a cantilever for that last rail to achieve this kind of magical hovering effect. And then we cut a hole through the roof and then we run internal wiring back to our point of interconnection to eliminate any kind of rooftop conduit, which I think is a tripping hazard and a fire hazard and an aesthetic hazard. I just don't like exposed conduit on the rooftop. I always prefer to drill a hole through the roof and go into the attic for cable runs. Let's do a calculation just for fun. Um, the calculation is going to be, you know, can solar generate more power than what the building needs to offset 100% of its electric use? And this is kind of interesting. If we know how much energy our solar array will produce, and we know that the wattage of our solar panel, so a typical solar panel today is 300 watts, 3 1/3 feet by 5 1/3 feet is about 18 square feet. If we know 1 watt produces 1.4 kilowatt hours per watt per year, then we know that this solar array will produce about 4,200 kilowatt hours per year divided by 18 square feet. That's about 23 kilowatt hours per year per square foot. And the typical residential building, and even 1 or 2 story tall buildings, whether they be residential or commercial, consume around 9 to 15 kilowatt hours per year. So on 1 and 2 story tall buildings, it is very possible, if you cover the roof with solar, to offset enough electricity to knock out the electric bill, provided that you have a net metered rate structure. And so then it's just, well, how many solar panels can you fit on the roof to maximize your electric bill, maximize the cost savings? So what I do when I'm looking at a site is I'm trying to keep the project pretty simple. I'm trying to line up, 1, 2, 3 roof surfaces that are perfect for solar, and then do nice, aesthetic, continuous solar arrays, that are cantilevered with internal conduit runs. That achieve this kind of nice, pleasant aesthetic. Another thing I do is I select all black solar panels. So uh, most solar panels have a little bit of a white backsheet to them, and you can get these kind of white lines, and then they have these silver frames. That can look good on a metal roof, but on a shingle roof, I choose an all black aesthetic. And so, if you really roll up your sleeves and do some bargain hunting, you can find name brand all black solar panels for 44 cents a watt, provided that you're buying a pallet or two. And so, when I'm planning my array layouts in low margin, low profit areas, I'm just looking at a rooftop and say, okay, are there 2 or 3 roof surfaces that I can fit 2 pallets of solar on? And if so, what are those 3 roof surfaces, whether or not they face south, east, or west? And I just fill it up. That's the project. Move on to the next one as far as simple, cost effective solar goes. So, what we're going to do now is show you an example of some design software. So I provide access to the recordings of these programs, so you don't need to worry about absorbing all of it today. I'll send you an invite later after the break. Okay, well, I guess we're not ready to do our demonstration just yet, but we will have that a little bit later today. So what I'm going to show you now is inside a solar software called Solar Design Tool. I'm not trying to train you on how to use it, but we're going to use the capabilities of this software to talk through the project permitting process. And so starting right out, this is, I used to hate the idea of using software to do my design work. I love the idea of knowing every calculation that goes into the project, but one of those factors is human error, and computers don't make the same mistakes that humans do. So if you can add computers to your design process, you will become a more accurate solar designer and make up for maybe the inaccuracies that are part of your own ignorance. So I think that a great way to learn solar is to sign up for some of the trials, free trials of these softwares, and then go through design examples during your trial period, and that alone will be great ways to bump up your knowledge beyond this class. But at any rate, we're creating a project, we're importing our project information, our site location. Now we have to input some additional information from our site. All of this information is great information to collect as part of a site evaluation. So the meter number of your electric meter, that is something you have to give the utility at some point in the process. Collecting that information up front just makes things easier. The kind of electric service. Are you in a small apartment that only has 120 volt service? Maybe. Commercial voltages range as well. So you need to know that for your what inverter equipment you buy. Uh, Solar Design Tools kicks it up a notch. They're actually putting in manufacturer brand names of uh, common brands, because they're going to create a permit document out of this. The rating of your electric service panel, the kind of connection of your electric service panel. If you don't know the answers to this kind of stuff, then your best bet is to hire a solar designer to do all this, preliminary project planning for you. But if you want to learn this stuff, going through every detail and knowing the answer for, well, what's the difference between a top fed or a center fed or a bottom fed bus bar on a service panel, that's stuff that is second nature to an electrician. So I know when I got into this industry, I was an engineer. I could get myself into situations where I'm being asked to be responsible for things that I don't know the answer to. Hiring an electrician to go through electrical basics is always a good thing. We have some classes with PDH Pro coming up on introductions to National Electric Code. So main breaker ratings, any other additional details being captured here. Um, is there an electrical sub panel? I mean, a lot of electrical balance of system questions. The site owner name. Now we're being asked, well, what version of electric code are we on? Um, I like designing to the latest and greatest code. Some inverter systems are only compliant with previous versions of code. We might talk about that in a minute. It's asking for the fire code setbacks. Are you designing to international fire code or national fire code? I wouldn't say one code is better than the other. They're all trying to aim for the same thing. What's your snow load? What is the wind exposure of the system? Are you on a prairie, or are there objects around to break up the wind? What's the risk category of the building? Are there people inside, or if it fails, is it a higher risk? Topology, like is it up on top of a high area and exposed or not? That's going to impact your wind speed, what the property grade is. Your wind speed 3-second gust is usually 20 miles an hour more than your prevailing wind speed. So all this is being factored in by the design software. The next step is to put in your address, and your Google Maps image comes up inside the software. And sometimes you can use different Google Maps images to get better clarity as to what you're looking at, so you can differentiate between a smudge and a plumbing vent. The street view can be revealing as well. It can provide whether sometimes you can actually see the electric meter, and so you can determine if it's an underground service or an overhead service. Not all from the comfort of your desk. So now we are tracing over in the software. We're tracing out our roof lines. And again, if you're staying 3 feet from the edge, maybe this is a little bit inaccurate. So maybe it's better to stay 3.5 feet from the edge, give yourself a little bit of wiggle room, and make the rooftop all the more accessible for the installer. But regardless, you're tracing the outline of the rooftop, you're telling it which direction the rooftop is facing, whether it's facing south or facing north. In this case, we're saying, no, this surface, this polygon faces south. We're putting in the roof tilt. Now we're adding in some restrictions. So we're saying, okay, we've modeled the south side of the roof here, and the north side of the roof here. Now we need to add in some restricted areas to say, don't put solar around these plumbing vents. And I would say around these plumbing vents is where the roof leaks occur. It's not the solar array that causes leaks in the roof. It's the installer not being careful with the other stuff that's already up on the roof. If you're filling in this whole area with solar and you're leaving this area empty, it's this empty area that becomes the walkway on the rooftop. So, if you're leaving empty areas because of plumbing vents, it's best to leave a lot of space around them, and then tell the installers not to step on them. But you can go all the way up to the plumbing vent. There's even plumbing vent kits out there to replumb the vents underneath the array and out the top. You can't do it for all plumbing vents, and there's some vent stacks that you want them open and accessible for maintenance. At any rate, the process is to map out the rooftop, identify the roof obstacles, and then at that point, you'll get into so we're talking a little bit more about the identifying. Okay, so here we're putting in where the utility meter is and where the main service panel is, so that it can calculate how far the wire run is between the 2 points. And that will factor in voltage drop, cable sizing, conduit sizing, and all these other code-driven design considerations. So it's asking for the least horizontal distance, which I didn't understand quite what that was, but basically if you divide any building into a rectangle, the smaller side of the rectangle is the least horizontal distance. It's asking for the roof material. It's asking for the decking type. And I think that is why I love solar design tools so much is because it's to get through the process, you have to be very detailed on the information you collect from site. So it's if you really want to start a solar company or do a solar design, these questions are perfect questions to answer during your site evaluation. Rafter spacing, rafter dimensions. And so finally, we have our array layouts for our different roof surfaces. And so the question is, well, what layouts do we want to use? And so in commercial software, they have the solar panels already in the inverter systems already programmed into it. So inverter manufacturers produce their own design tools so that you don't have to use proprietary software. You could find the solar module specification sheets online and do all the calculations by hand. Commercial software makes it easy so you don't have to do any of that stuff. We're just telling it what solar module we're using and what inverter system we're using, and it's taking our roof surfaces and our setbacks and then just saying how many solar panels can we tile into the remaining roof space. And there's some finer elements to that. Do you want to go with a landscape orientation, or do you want to go with a portrait orientation? And on a shingle roof where the rafters are running up the rooftop, the rail is going perpendicular to the rafters, and then the modules are laying perpendicular to the rail. And so installers on shingle roofs will tend towards portrait orientation, and installers on metal roofs where you have purlins going east-west across the rooftop rather than rafters going north-south. A metal roof will tend towards a landscape orientation. But the point is you can do both. You might, to do the orientation that doesn't naturally fit the roof, you might spend a little bit more money on racking, but racking is a small amount of the budget to begin with. And sometimes by doing a landscape configuration, you can fit more solar panels than doing a portrait orientation. Sometimes landscape looks a little bit better than portrait. Sometimes portrait is just fine. Portrait is the default in the United States. Now, when I'm doing my project designs, I'm opening up that spec sheet and I'm determining how many solar modules are in a pallet, and I'm doing my design proposals not based off the rooftop, but based off how many solar panels come in a pallet. So I'm bidding customers, a small system that's one pallet, a medium system that's two pallets, a large system that's three pallets, and simplifying my project logistics that way, because when I do projects, I'm a small outfit, and so I don't have the warehousing capability that larger solar installers might do. But then again, I'm also not trying to cover every single square inch of the rooftop with solar. Even though the design software is telling me everything that's capable, I might go in and scale back my array. It just might not be worth it to install these two panels by themselves or these two panels by themselves. Simplifying the array look can improve the aesthetics. These are design decisions that the designer himself is going to have to make. Um, Really not enough time to get too far into this, but the solar module manufacturers indeed have rules about where the clamping system that connects these solar arrays together, how those clamps fall into the racking that's underneath. We don't really have time to get into those details, but engineers, you'd be interested to note that they do have load data for various clamp zones. And say if you're in a hurricane zone, often you'll just put an additional stick of rail underneath and give the module additional performance, and you'll see the module rating go up. And also you can do, fancy installers will start doing like common block layouts for their solar arrays, which can be even more dense than other configurations, and in some cases look better. Like a really irregular roof, a common block layout can look just as good as a rectangular solar array. And so here I've said, okay, well, I could cover, the south and the east and maybe the north side of the rooftop, but the customer really lends itself well to a two pallet installation. So can I fit 50 solar panels on my rooftop? And if I can fit 49, I can say, okay, well, these two panels by themselves stink, so I'm going to take them off. And this panel by itself is a little awkward. I'd rather have the solar array visually be going inward. And so I'm making some minor adjustments. And so I could fit 52 solar modules between these two roof surfaces. I know solar panels come in pallets of 25 for this particular panel. And so I'm aiming for 50 panels, maybe sometimes 49, because having an extra solar panel is never a bad thing. And we're going to take our break in just a minute. I'm going to go till 10 till to finish out this section. But essentially, we've here we've opted for a different 50 pallet configuration that uses 3 roof surfaces because it's a little bit easier of an install, and maybe on this complicated roof section it lends itself to better site accessibility. And so we're going to come back to Energy Toolbase, but we can just see how instead of you actually hand drawing these arrays on the rooftop, the computer software models it for you. So let's see. So I guess we're already an hour and 45 minutes into this thing. Let's take a half an hour break, and we'll come back at 2:15 Eastern time, and then we'll pick back up from there. So, we're going to do a 30-minute break. And then we'll be back at 2:15. No, I don't have to know. I'm taking my break. They need it, yeah. Um, sure. Oh, food scale.
which is like, what should be doing instead of trying to charge like $150 a month or whatever it is, you know. But I like going to get it. I don't want to go to get it. You know, so anytime I go out. So basically, the short version is your beer didn't get added on, but other than that, we're in pretty good shape. I got some lamb.
Wonderful.
What? Why are you stressed out? You have a two-person class.
Three.
Oh.
Someone signed up at the last minute.
I think they should have run an email.
You think they should have what?
Run an ask blast. Right before? Like 2 days before or something like that?
Well, it's just something this month before. I don't know about that, but
See, I think they should try and catch people anywhere they can. You know what? There's one tomorrow that's only $80. What do you think?
yeah.
Well, I was like, people don't know what their schedules might be like or whatever. Well, they can go.
Wow. Those are nice ones. Raspberries really are the best berry.
Truly. They're great by themselves, but they're also great for anything else. And obviously it's great to cook with. Right, thanks for coming out. I just made a half a pot of coffee. You want to come?
Really good for your flow. Yeah. Wow, this is awesome.
Right? I'm starting to get to enjoy like seeing what can this thing do. So this time I used the last of the whipped cream. But then
Of the whipped cream.
yeah, remember we were using for our coffee yesterday?
Oh, the heavy cream.
Yeah, heavy cream. Heavy whipping cream. And so then I had to add a little water because it was kind of too dense. You could tell it wasn't. But now I know the batter well enough to know what to be like, so I just added a little bit of water. But then the bubbling out of I used the last of the strawberries because they were a little bit. No, they weren't real sweet.
Oh, these are strawberries?
No, they're both.
Oh.
Well, the rest of the blue raspberries and the rest of the strawberries. There's only 4 strawberries left. So I was only going to do the strawberries and Eddie's right underneath me with this toy. I can't find a bag of them. It's not. I know I brought it here. There's so many more. So that bubbling up with the fruit, I think, is nice with like I didn't make those holes or anything. That's just the result of having fruit with moisture in there. Which is why they're supposed to use like dried out like blueberries and stuff, because also you don't want to like liquefy your mouth. Liquefy your mouth. So let's see. What's happening? What's happening?
Well, I'm hoping. I need to figure out if Athena will have it or whatever.
Oh, yeah, I didn't see her leave a message, so. I made a family cover post, and the whole family likes it. Of course, none of you really post about Amy anymore. Pac barely does anymore, and you don't, and your mom doesn't, and Amy doesn't.
Yeah.
It's because you're all dicks.
All right.
What?
I'm nothing. I'm stepping into the blue.
Okay, so I'm not gonna pour your coffee, so you can.
Okay. We're going to get started again in about 2 minutes or so. Hey, Jerry. Sounds good.
Did you get some coffee?
All right. Let's get back going then. So, shade analysis is kind of one thing that computer modeling of solar is really great at. Even the most robust on site shade analysis is not perfect. It used to be we had to take this device called a solar pathfinder actually up on the rooftop. And the way this device works is there's a chart underneath it from 8 a.m. to 4 p.m. You're looking for no shadows in this. So like up here, what this is saying is in the summertime months, this tree is going to mean that the solar array is not going to turn on until 8:30 or 8:45. That's acceptable. That's okay. And then also by the time this house becomes an issue, we're going to be in wintertime months when the array is not going to be turning on till 9:30 anyway, so that if the array will be on by 10, it'll be on by 9:30 in the wintertime, and then be free and clear pretty much for the rest of the day. And so you would use this device and walk the whole roof to determine where solar would be good at and where solar should not be located. Of course, trees grow over time, and so maybe you have to allow for some future tree growth, and at that point you're just kind of guessing anyway, even though you're on site and being very precise. So computer modeling is a bit of a guess, but as what we'll see for shade modeling, it can result in very good calculations. So basically now we have this tree, and the tree is casting a shadow. And just like PV Watts is running a calculation for every single hour of the year, your computer software will simulate the sun's position for every single hour of the year and translate that into performance loss for every solar panel up on the rooftop. And because we're using microinverters or DC optimizers, it's only the shaded solar panels that get affected. And so basically, basically we're running a PV watts calculation for every single solar panel on the rooftop, and then their helioscope takes it a step further. They're calculating the voltage drop for every single solar panel on the rooftop, and so it becomes a very accurate way to model shade. And the advantages being in a very short amount of time, you can give the client a proposal for the entire roof, just the south side of the roof, and then different proposals for whether or not they have the tree there, or if they chop down the tree. They can say, okay, well, you're going to gain precisely this much electricity if you chop down the tree, and give that, make that decision to the customer. Now, I can tell you from personal experience, most customers, even if they're all right, if you say, well, shade, you can either keep the tree and produce 10% less, or you can chop the tree down. Initially, they're going to say, well, let's just keep the tree. And then after the solar array is built, they'll say, I don't like that shade. Why'd you put it where the tree is? And, then maybe the answer is they have to chop down the tree. Just because the solar arrays today can be shade mitigated, it doesn't mean that solar is meant to be in the shade. What that means is the shade only impacts the solar module that's shaded and not the rest of the system. And so here we're doing kind of a surprising impact of shade modeling for this tree, because the software is performing a performance analysis for every solar panel on the roof. It might at that point say, well, some modules are more affected than others, and it turns out it's the solar panels that are closest to the tree that are the least productive. So there's some solar panels on the north side of this building that are actually more productive than solar panels on the south side of the building, assuming that the client keeps the tree in that location. So that's where a 3D computer model can really come in and guide the design process, because otherwise there's just too many calculations that would go in for you to make that decision on your own. And so because it knows the panel spec sheets and the distances between the panels and the service panels and equipment, it can calculate voltage drop, it can calculate amperage, so it can calculate wire sizing. And not all of these softwares will put that information into a design document. So Helioscope is not trying to generate permit plan sets. They're just trying to assist you with your array layouts and preliminary design. And they don't want the liability of going through a complete plan set. Whereas other, solar design tool, they don't have a 3D shade modeler built into their software. They're really better for, once you know where the array is going to be, how to generate a plan set with it. But now we're going through some screenshots of a company called Helioscope. And Helioscope is just useful for rapid modeling. Like solar design tool, you sketch out the roof, it fills it in with solar panels, but then it has some 3D modeling capabilities that we're going to look at in just a minute on a video. This is a computer capability that is part of Aurora Solar software package. Sometimes if you log into your utility meter account, sometimes they have stuff like this in your utility account. But basically what they're saying is, we don't know what your actual load profile looks like. You have to install a monitor in your electric service panel to actually see what your electric load looks like. They're guessing at what the electrical load looks like. So they know, hey, we know at the start of the month and at the end of the month how much electricity you use. And so we're going to divide that into the start of the day and the end of the day for every day in the month. And then we're going to ask you a survey, And based on, if you have a swimming pool, an electric tank water heater, hot water tank on electric, or so LED lighting or incandescent lighting, an electric vehicle, depending on your location, whether you live in the north or the south in terms of temperature, it will without knowing what your actual load profile looks like, it will take a guess at that. That's pretty useful in off-grid design, when you're or for modeling solar production versus how much will stay on site versus off site. Really not that important for being introductory solar class, so we're going to keep moving, talk about some other functions. Okay, so if you took this solar program in years past, we would say go into PV watts and find the day where you get the most output out of your system, which is generally in the springtime when you have sunny days but cold operating temperatures. And we'd say, okay, out of this 1,000-watt solar array, only 875 watts are coming out of it at its 1 hour of maximum performance. And so we'd say you can undersize your inverters, which are the output of the system, compared to the input of the system, which is the solar array. So if you have a 10 kilowatt solar array, you would look for, a 9 kilowatt inverter, and you would still capture every single electron coming out of the system. That kind of right sizing is less important today because inverters have dropped in cost as well as solar panels. So the cost difference between a 9 kilowatt inverter and a 10 kilowatt inverter is not anything significant anymore. Let's revisit our inverter selection knowledge. Solar panels consist of individual cells. The industry calls these things solar modules instead of solar panels. And the solar panels up on the rooftop, one array might comprise of multiple circuits. In the industry, we call these DC circuits strings. And so the basic type of inverter is called a string inverter, and it's for circuits of panels. This is just one circuit, but a string inverter can take multiple circuits of solar panels. So the solar panels are wired into individual circuits, and those circuits are wired directly to the string inverter with nothing in between. Fire code now requires individual boxes to go behind each and every solar panel on the rooftop. So the problem with string inverters is this home run conductor is uncontrolled. Just like a solar panel is always on when the sun is up, this home run circuit conductor is always on a string inverter. So National Electric Code has made us go and put little boxes behind every solar panel that stop the electricity at the solar panel itself so that we can control these home run string conductors. And so really on rooftops, you don't use string inverters. String inverters are cheaper, they're good quality, they're great on ground mount systems, but fire code says you got to kill the electricity at the solar array and actually at the individual solar module. And so now we have to install these individual boxes behind each panel. These are called microinverters. So instead of having one inverter for the entire system, you have one inverter for every solar panel on the rooftop. These were actually not developed for control. These were developed for shade. It used to be on string inverters that one shaded solar panel would take out the entire circuit. And so microinverters could allow a chimney to shade one solar panel and the rest of the array remain unaffected. But they also have the secondary benefit, and now it's the primary benefit because string inverters have also gotten better at managing independent circuits. They used to just group all the circuits together, and if one bad thing happened on one part of the circuit, it would impact the whole system. The whole system would go offline. So it used to be you had to avoid shade like it was the Black Death. Now even string inverters are a little bit better at shade mitigation, but you still don't have the module level control for fire code. And so microinverter said, well, we'll just have an inverter for every single solar panel, and it'll be AC output up on the rooftop. And then another competitor came to market called Solar Edge, and they said, we're going to put these individual boxes behind every panel on the rooftop, but they're just going to do DC to DC controls, not DC to AC. And we're going to keep the DC to AC controls on the inverter on the ground, because buying one big inverter is cheaper than buying dozens of smaller inverters. But we're going to take some of what was inside here and move it up to the rooftop to comply with fire code and also to do some shade optimization. So the DC optimizer system is cheaper than the microinverter system. And so most solar installers on rooftops prefer the DC optimizer system out of all other kinds of systems. But if you're new to solar for a do-it-yourself project, for your first time project, or if you want to use an installer who's a regular electrician, not a solar guy, sticking with the microinverters is an easier install. It's a little bit more plug and play. You don't have to worry about the DC side of things. A regular electrician doesn't know anything about the DC side of things. They feel more at home with microinverters. And so because of this regulation called rapid shutdown, which requires you to confine all the electricity to within the array boundary, but on top of that, shut down the electricity to the individual solar panels themselves on the rooftop, that's called rapid shutdown. Basically, string inverters are fading out of solar design, and DC optimizer systems or AC microinverter systems are now in style. And so to see if your microinverter is compatible with your solar panel, you just go to the microinverter manufacturer's website. They have sizing tools available. You enter in your module specification sheets, and they give you a thumbs up or a thumbs down. You know, here, that's such a simple process that this particular microinverter manufacturer says, hey, for this particular microinverter, you can have, here's the voltage and here's the amperage. And we can see it's like, 1 amp per microinverter. We're going to come back to that. If you were not using commercial design software to determine how many modules go on a circuit, you would use manufacturer provided string sizing software. So here we're putting in our temperature, regional temperature conditions, and then we're selecting our inverter. And remember, we would look at our array size and try and find an inverter of the same size or slightly less. And so you pick out which inverter within the manufacturer's product line you use. You pick out the solar panel that you got good pricing on, so you're going to use that. And then the sizing, the manufacturer sizing software does all the calculations to tell you all the possible configurations of how many solar panels can fit on how many circuits. And so if we say, okay, on the first input of our string inverter, we can do 2 circuits of 10 solar panels. Well, then the other input on the string inverter would adjust and tell us how many remaining. It might, after we select our first option, it might tell us, oh, you can do only 1 circuit of 10 panels remaining. But the point is, the manufacturer's string sizing software will tell you how many panels can fit onto how many circuits. It's there to guide you for that. And this is an example for the DC optimizers where we are inputting the solar panel we're using. We're putting in how many solar panels are on the roof. We're putting in our tilt angle and orientation. And elsewhere we put in our location. I just didn't make the graphic. And then it's telling us, well, okay, well, for those panels, you're going to use, in 132 of them, you're going to use two 10 kilowatt inverters. They're going to have 3 circuits each, and you use this P405 optimizer, and there's going to be 2 optimizers for every solar panel on the rooftop. And so, we know based on having an array layout and a solar panel, we go to the inverter sizing software, put in that data, and it tells us which inverter to use and how many optimizers to use. So the software, the manufacturing software, even if you're not using commercial design software, you're going to be using software to guide the design process. And this stuff is available free from the manufacturer. The manufacturer wants to make it as easy as possible for you to design a system using their products. One of the finer notes of solar design is, now that you know how many circuits and how many panels, determining how the circuits are actually going to fall on the rooftop can save you some time. If you have broken up roof surfaces, it's going to be confusing because this circuit might have to tie into this circuit, and then this larger group might be on its own circuit. What I really like doing is starting my circuits at the end of the array and moving them all the way across the roof and ending them on the other side. But sometimes you don't have that convenience. But as a designer, this circuit array layout can get really confusing. So, I like starting at one end. So this is like this is a 60 panel configuration, and here we're modeling 6 circuits of 10 solar panels. And so the circuits in our array layout are going to start at one end and then just move all the way across. And then the next circuit is going to start and move all the way across. And that is kind of a logical layout that a solar installer who doesn't know anything about this project, if they get up onto the job site and look underneath the array, they can say, oh, I hope that's how the circuits are laid out, because that's going to make it really easy for me to check the connections at the ends of the circuits without deconstructing the whole solar array. What many installers will do, if given the choice between 6 circuits of 10 or 4 circuits of 15, they'll say, well, 4 circuits of 15 are 2 fewer circuits. That's less work to do. And so we're going to do 4 circuits of 15. And so instead, the way they would wire it is start here and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then get to the next circuit and do 3, 8, 13, 14, 15, and then get to the next circuit and do, 12, so 3, so 15, so that should have ended right there. And then they get to the next circuit and do the same thing. And what happens is your circuits start to get lost throughout the whole array, so that by the time a solar installer who's not affiliated with the project comes to do some maintenance work, they have no clue where the circuits start and stop unless they're lucky enough to have a map that tells them. So having a map that tells you where the circuit layouts start and stop is important. And Solar Design Tool, and not all, but some of the software indicate that. And let's talk about interconnection for a minute. You got 2 options. you can either go in between the meter and the main breaker, like where the power lines come into the property, but literally on the customer side of the utility meter. So that utility meter is outside the home and there's power lines that go between it and inside the home. You can tap on to those conductors. That's called a supply side connection. Otherwise, you can wire the array up to your service panel. That's called a load side connection. The difference is on a supply side, just like how the power company can feed 200 amps of power on a 200 amp service as regulated by that 200 amp breaker, it doesn't matter if it comes from the utility or if it comes from the solar array. There's no more than 200 amps is making it through that main breaker. So if you have a 200 amp electrical service, that means these conductors are rated for 200 amps. That means you can connect a solar array that's as large as your electrical service. If you have a 200 amp service, you could do a 200 amp solar array. In most cases, that's overkill. Most homes only need a 40 or 50 amp solar array, but you combine a solar array with a battery inverter, with an electric vehicle charger, those things start to add up. And one way to connect them to the property is to land on these main conductors. If you land on the load side of the panel, you don't get 200 amps of capacity. You only get 20% extra because you're still feeding the power from the utility. And so you're actually overloading or supercharging the service panel because this is a 200 amp panel and you're putting 200 amps from the utility and 40 amps from solar. You're feeding a 200 amp panel with 240 amps of feed. So National Electric Code says you're only allowed to do that when you connect the solar array on the opposite end of the utility feed. So the utility comes in at the top, the solar array comes in at the bottom, and that gives you an extra 20% capacity. It's called the 120% rule. So on a 200 amp service panel, without making any other changes, if you're landing on the breaker on your service panel, you can land a 40 amp solar array, but it has to be at the bottom of the service panel physically. The physical breaker has to be at the bottom to get that extra capacity. Otherwise, the power from the array and the power from the utility could combine and overload the bus bar. The only way for it not to be a fire hazard, since you're supercharging your panel, is to locate the power feeds at opposite ends that more evenly divides up that load. And that's because your home, your breakers have more than 200 amps of breakers on it. So if all the devices in your home were on at once, normally they're protected by that 200 amp main breaker. So if we connect a power supply that's not throttled by the main breaker, then we could be pulling more power through the electrical service than what it's rated for. So you only get an extra 20%, and you only get that extra 20% if you land the solar breakers at the very bottom down here. Now, sometimes you want to keep the installation outside the main electric room. Now, there's not really code violations going on in this room aside from storage in front of the electric service panel, but it's a messy room. And so, the inspector may come in here and say, we want you to clean up a lot of this work, even if it's not your own. A good way to keep the inspector outside the building is to say, okay, well, where does the electricity come in to these two electric service panels? Here's outside the building. The electricity comes in from the meter into those two panels through these two boxes. So long story short, on this project, we said, okay, our array is only large enough to connect to one of those two panels. So we powered down the building on a weekend. We pulled the conductors out of the main service panel, out of this box, and then out of that box. And then we installed a larger box to work in. We put those conductors back through and then powered the building back up. And that was a 2-hour job over the weekend. What we're doing in this case is a supply side connection. We're intercepting the conductors between the meter and the service panel inside the building. Our tap is going to be made inside of this box. So our microinverter circuits are coming down from the roof, landing on an AC distribution panel, running through a knife switch disconnect, and then running into our tap. And here's what that point of interconnection actually looks like. So these tap conductors, one cable goes in, another cable goes in, and the tap is made inside. There's a couple of different kinds of tap connections, and which tap is appropriate is really something that only electrician familiar with their site is going to be able to tell you. But the short of it is, this big heavy feeder cable from the utilities is difficult to work with, and you need someone with really good hand strength and eye protection to work on that, because you're like wrestling with those cables while you're landing them into the taps. They need to be made correctly. They can't pull out. It's a simple job, but it's not an easy job. That's making these tap connections. The pierced insulating conductors are really easy. They just go around the conductors and crimp down, but you have to be able to get enough spacing around the cables. The tap connectors are very basic. You just put the cables in and then tighten them down. But it takes so much time to cut the cable and prepare the jacket and to get it fit perfectly in. And then there's some nuance on where these actually lay out in the box, because they'll interfere with each other if they're right next to each other. That kind of work, I hate it when my client is looking at me over the shoulder, tapping his watch when I'm wrestling with these cables, because it looks from behind, it looks really simple to do, but it's not. You have to plan it going in, and you have to have the hand strength to execute it, because you're not dealing with a lot of space unless you're replacing the conductors. So now we're back in Solar Design Tool, and we're doing a microinverter array. And we saw this is an older generation of microinverter that's 0.9 amps. So in our spec sheet earlier, we saw the microinverters doing 1 amp, but it's 0.9 amps. And these microinverters land on 20 amp breaker slots. And per AC wiring, the amperage is oversized by about 25%. And so what that means is we can fit about 17 0.9 amp microinverters, and that'll get us to 15.8 amps. And then we oversize it by 25%. We put it on a 20 amp breaker. And so in the sizing software, you don't have to know any of that stuff. It's just telling you, okay, I use this microinverter in this solar panel, and I can fit up to 17 microinverters per circuit. So this row is 17 modules long. That's going to be circuit A. This row, circuit B. And then maybe, since I can't do 20 on a circuit, I do, these two smaller circuits on one, and then this larger circuit on another, and I have a 4-circuit system. So we're almost done with our solar design tool example. we've edited the module inverter configuration. You can go in and work on balance of system material. So if I have 3 circuits out of 4 that are using 1 inch conduit, and I have one small circuit that's only using 3/4 inch conduit, I might, not always, but I might make everything 1 inch conduit, upsize my conduit to make my project material a little bit more simple. You don't just want to do that arbitrarily because larger conduit is more expensive, and you get much larger than 1 inch, you can't bend it. But some other things that Solar Design Tool does: material reports lists, single line diagram generation. Let's take a look at some of those features. So here in the survey, it's asking us, do we do a supply side connection or a load side connection? So do we go in between the meter and the service panel, or are we going into the breakers? And that's going to change the electrical drawing. Are we having a meter for the solar array or just using the utility meter? That's going to change the electrical diagram. What kind of utility disconnect are we having? What is our grounding system? In 4 hours, we just don't have time to cover all of those details. We have a whole series of solar webinars distributed with PDH Pro. But what we have right here is our interconnection method. We've said it's a supply side connection. And on the line diagram that the computer generates, so you're not drawing this stuff in CAD, this is automatically generated. What we see here is a solar production meter. It's included. We have a combiner panel that's included. And then here we have to the main service panel and to the grid. So this is where our kind of supply side tap is being made. I'm going to talk about rooftop transitions in a minute. In the interest of time, we can't go into, I wanted to give you course material that has a lot of detail. Shoving it all into a small period of time doesn't always work, but it's looking at conductor D ratings for different D ratings for if the conductors are within an inch of the rooftop or not. And at every single kind of step along the way, it's asking about our conduit runs. Are we doing an internal run? Are we above the rooftop? Are we doing direct burial? What is the conduit type? Are we in metal conduit, plastic conduit, a flexible non-metal conduit, flexible metal conduit? Solar Design Tool is pretty thorough. It's only like Achilles heel is that it's really just for smaller residential projects. It doesn't scale up to large projects. So most residential projects, it's going to be a great one. So it's looking at things that you would have to look at as an electrical designer, like the temperature rating on the terminals, and then the length, so that it's doing its temperature and ampacity charts correctly. And the end result is you get all of these automatic reports. I really like their National Electric Code report that walks through every calculation that an inspector is maybe going to want to look at when inspecting to make sure you didn't make any mistakes. The computer doesn't make mistakes. It's the human error element is where the mistake is most likely to come into play on a solar job. But it will generate, here's something that's neat. It's because National Electric Code governs the rules that size your conductors, and because the conduit size is driven by rules based on the size of your conductors, it's calculating how many conductors are inside the conduit and what the percent fill is, and every other electrical calculation that's needed as well. Things like circuit level voltage drop at each point. So you can say, okay, well, maybe the voltage drop, it really has to do with, this um, this particular circuit. And so maybe if this is already upsized to number 10, I'm just going to make all of these number 10 and get rid of some voltage drop. But by the time I get into my number 8 kind of final circuits, the voltage drop is so negligible that upsizing any further is unnecessary. Finally, we get to the reward for our effort, which is the single line diagram. This is a map of the electrical system. It's not really showing physical layouts, but it still is going to reveal things like indoors versus outdoors, electronic components. And this type of document is computer generated. So to look professional in front of the permit office, inevitably you're going to have to get some software involved. That's just the days of doing the one line diagrams on Microsoft Paint and just showing 3 circuits of solar panels and an inverter and that's it. That doesn't reveal expertise like maybe it did 12 years ago. So now, the more professional you can present yourself to the permit office, the more likely the inspector is going to say, you know what, you're allowed to do this work on your own house, so go for it because you look like you know what you're doing. Whereas to someone else, they might say, hey, okay, maybe your state allows you to do electrical work on your own house, but we don't know this solar stuff very well, and we don't trust you to know it. You need to have a solar designer or a solar installer help out with this. So, Solar Design Tool is the only software I know that does a full National Electric Code report that you can just print out and include in your permit package. The other softwares, perhaps wisely, are trying not to be your electrical designer. Um, and I think Solar Design Tool, it has its limits too. It doesn't do this stuff for large commercial projects. But in terms of learning National Electric Code, this is the best report because it's going to call out every single calculation with code references on what's needed in solar design. So if you want to really learn the brass tacks of solar design, starting with design software and then reading the documentation and backing into it is a great starting point. I want to make sure we're going through all the lectures. So what we're going to do is keep going with the lecture content, and then we'll talk through some video demonstrations at the end. But here's some solar attachment points. There's the short of it is there's hours we could talk about this stuff, but the short of it is there's a solar racking system for every roof type. Membrane roofs, tile roofs, Spanish tile, every single kind of metal. You can even use a tile replacement on a cedar shake roof, although I wouldn't put solar on a cedar shake roof. I think it's a fire hazard, but you can. I mean, it depends on your installer. Most installers who don't have to take every project that comes their way are in a little better position than those that do. But it's kind of funny, and if we had all day to talk about the engineering nuances, of racking, there's a metal roof system that's real popular that clips onto a standing seam. The alternate is to use a system that screws through the metal rooftop. And so most customers, the idea of screwing holes through metal really freaks them out, and they would rather have a roofing system that they can just clip to. But structurally, being able to take that lag screw and go all the way into the rafter is so much stronger than clipping onto the rooftop, because it's not the clamp that's the failure point. It becomes the interface of the standing seam metal rooftop to the rest of the roof. And I'm not sure if we're might be skipping ahead a little bit, but ultimately I use manufacturer racking design software even when I'm using commercial software um, that I have to pay for. I'm still going to model the array in the free manufacturing software when I'm done, because that will tell me the forces that are on my individual racking points. So how do you calculate that stuff? Well, you use the computer software to tell you the answer to make your life a lot easier. So the way solar racking works is you are lag screwing into rafters, you're flashing that attachment point, you're bolting to some rail, and then you're clamping the solar panels onto the rail. And there's clamps that go at the very end that clamp that last bit of solar panel onto this rail. And then there's clamps that go in between two solar panels, and these are called mid clips, and the ones that go at the end are called end clips. Not very creative terms there. And kind of on a finer installation note, the best top of their game installers understand that hitting every single rafter as you go across the rooftop is best structurally, but the spacing between rafters is too short compared to what the span of the rail allows. And so the very best installers will actually stagger their attachment points going across the rooftop so that every single rafter is hit as they're going across the roof. Entry level installers will just go all into one rafter and then skip over a rafter and then go all into the next rafter, which is generally okay too. It's just not as good, and it's once you know what you're doing, there's no added time really to stagger your attachment points. And then I try, so this is like the optimizer that goes behind the panel. It just mounts to the rail directly right behind the solar panel. I like selecting my racking based on integrated cable management. Um, you can get leaves, you can get pigeons, you can get squirrels nesting underneath the array. And while there are accessories called an array skirt to protect the array, nothing gives me better security at night than knowing that all of my cables are nice and tucked away and protected inside of my solar rail rather than being strapped to the outside of it. These are just nuances that you'll get. This photographed rail up here, it doesn't have a large enough channel for the cables to be tucked away inside of it. It depends. There's problems with cables going inside the rail too. You gotta drill out little drain holes for when water gets into here. So in a manufacturer provided racking software, you're basically taking your array layout and replicating it inside the racking sizing software. So how many solar panels, how many rows of solar panels, how many subarray sections, and whether or not it's in portrait or landscape. Here's a different manufacturer software where you're basically recreating the array layout. And so, here's our skylights, here's our little dormer or yeah, dormer. And then otherwise we're just taking our array layout and replicating it within the racking software, and that translates into, after you input your environmental conditions, your wind speed, your snow load, your exposure category, questions we saw earlier that the commercial software was asking us, our racking manufacturer free software is asking us those same questions. And ultimately, what we get is things like the span that the rail can take between attachment points. Um, Maybe you don't want the thicker gauge rail with the longer span. If I'm doing 4 foot on center staggered array layouts, I don't need a rail with an 8 foot span. I might use the cheaper rail that has the shorter span because I'm not using the length of the span to begin with. And the cantilever distance is nice too, because that tells you, when you're trying to locate the last attachment point, how far in to the perimeter of the array can you go. It starts to get a little bit more constrained when you go all the way to the corners of the rooftop and you're using the thinnest gauge rail. You start to not have too much space to tuck the rail underneath the array. And then finally, we get to our force load diagrams. And this is where we, in a longer class, we would have a discussion about can you screw into the rafter versus can you just attach into the decking. And it's a similar discussion to can you just clamp the solar array onto the top of a standing seam metal rooftop, or do you need to screw through the roof into something more solid? And it turns out that it depends on your wind speed. So if you're at the corners of the array, you get higher forces than in the interior of the array or in the interior of the rooftop. And so there are systems that are designed to just screw into the decking instead of the rafters, but you can't put them at the edges of the roof line because at the edges of the roof line, the wind speeds are too great. And so, if we're structural engineers in this audience, so we can understand the importance of those things, most solar installers say, you know what, I'm just going to stay 3 feet off the sides, and I'm going to go with a 4 foot on center attachment foot span, and that's going to be over engineered, and that's going to be just fine. And by putting the racking information into our software, the output is a bill of material. And what the value of this is, solar is a custom design. And if you want to work the supply chain for material discounts, if you can go to the vendor, even if you're just buying the solar panels, the racking, and the inverter, if you can go to the vendor with a line item list of all the material you need to buy, that vendor is more likely to work with you having never worked with you before, regardless of your industry status. If you can make their job easier, then that's what allows you to buy from the same distributors that I buy from. These distributors, they want to sell to everybody. It's not a closed supply chain like in other industries. But you got to be able to, if you can show that you've done some legwork, you can get further up that supply chain than just asking the solar installer to do all of this for you. And so the way I price out solar panels is I go online to multiple online solar vendors and I try and subscribe to their newsletters so that they email out the pricing that they send out to installers, not necessarily the same pricing that they post on their websites. And if I see really good pricing in that newsletter, then I'll say, well, I'm doing a project this month. I want to use that panel because it has a good price. How many panels are in that pallet? I go to my commercial design software, I design a 1 or 2 pallet system, and then I email the vendor. I say, I need these specific items. I know you carry them, and for this price, let's get a sale done. And maybe that installer, that price he sent out was just for, installers already signed up in their installer network. If you show them you're serious, 9 times out of 10 they're going to greenlight the sale, even if you're not already set up in their program. So my favorite upgrade is all black solar panels. I also like clean and even solar designs. You can see in this picture, the is a new roof, and they went with black vent stacks to blend into the roof. And whoever did the site evaluation remotely missed this vent stack right here, because very obviously that solar panel was supposed to go right in that area. I hate it when solar panels just stick out like that on their own. I what you want is a nice clean black rectangle on the rooftop to preserve your aesthetics. It otherwise this is a fine looking solar array. Okay, well maybe the you can't see the roof when you're in the yard, but if you go far enough away, turn around, you can look up and see, rooftops. So there are some products out there for replumbing the vents on your rooftop as an alternate to having an ugly solar array. Um, I'm not a big fan of solar shingles. They're very hard to find. I don't think they look very good. They're expensive. They're more difficult to install. Basically, when you're putting solar shingles on a rooftop, you're installing hundreds of really small solar panels instead of 2 dozen really large solar panels. And it's just not a good product. And people, installers, get really mad at Tesla for saying they have solar shingles, and then they suck up a lot of interest, and then they don't deliver. I think that compared to an all black aesthetic symmetrical appearance with internal conduit runs, I don't think that these arrays look worse than a solar shingle array. And in fact, I think irregular solar shingle arrays can look just as bad and cost substantially more than their traditional equivalents. We talked about the cantilever span. We talked about the racking being tucked up underneath the solar array. The last thing is, well, how do we actually do that internal conduit run? Sometimes internal conduit runs are way easier than running the wires through conduit outside the roof, over the roof edge, around the roof edge, tucked up underneath the soffit, and down to where the point of interconnection is supposed to go. Sometimes it's a lot easier just to drill a hole through the roof, run some flexible pre-wired conduit through the rooftop, and come out right where you're supposed to go. Sometimes that's much easier. Now, this flexible pre-wired conduit is more expensive than doing it the other way. But then there's the labor and hassle. And then furthermore, the ugliness, and then it's a trip hazard, and it's exposed to extreme temperature differentials. I just think, and bugs and pigeons and squirrels. I just think there's so many reasons just to go into the roof with your conduit run that if you can do it, you should do it. This is called a Sola deck. It's a specialty box that can get flashed into the roof deck, and this is where the hole is for drilling into the attic. And the solar cables come in and they land on top of the breakers. But there's other flashed products for making holes in the roof and coming out the other side in a workmanlike manner. Not all of them are solar specialty products. Although I would caution you, the plumbing boots like this that you get at the box store are suitable for plumbing vents. So they're for inch and a half, 2 inch pipes. Most solar, the holes you're going to drill are smaller than that, and so the size of this hole on your traditional plumbing vent is too large. So this to make the rooftop transition and your rooftop transition box. Generally, that's a specialty item. Another special order item that I buy, but not through solar vendors, is this pre-wrapped, just through electrical distributors, this pre-wrapped cable. Solar, like the DC optimizers, is a DC system. DC wiring inside a building has to be in metal. AC wiring inside a building can be Romex. It can be in that flexible plastic covering, and you can just run it wherever you want. DC has additional physical protection requirements that, as far as I can tell, it's discrimination. There's no good reason why a power conductor that's DC needs more protection than a power conductor that's AC. It's just it's a weird part of code that is not well explained, and it's confusing because it has nothing to do with the ground path of DC versus AC. It has everything to do with physical protection. But at any rate, DC needs to be physically protected. There is a special cable called MC cable. It stands for metal clad cable that you can get, and it's expensive. It's like $3.50 a foot. But what it allows you to do is drill a hole through the rooftop, stub up your metal cable into your transition box, and then just throw the cable through the attic and come out the other side where you need to go. It's wonderful. It's installers might call it magic cable, even though it stands for metal clad cable. I will upsize this cable from number 8 to number 6, even though it's more expensive to do so, because that gives me an upsized ground, and a number 8 ground is the smallest ground cable that you need to run up to the rooftop to ground your solar array. So I get either 6'2" plus a ground MC cable or 6'4" plus a ground, and that'll give me a positive and a negative for one circuit if it's 6'2", or 2 positives and negatives for 6'4". And so generally speaking, if I have a 2-circuit DC optimizer system, I'm running a 6'4" MC cable up to the rooftop. And if I have to go from one section of the roof to another, I'm jumping a single circuit in 6'2". And maybe that's a little bit more electrician speak for this program. But when you come out the other side of the rooftop, you can transition directly into rigid or into EMT, or you can put a box there and do the transition there as well. MC cable is only rated for damp conditions, not wet conditions, so you have to transition into something that's fully enclosed once you get outside the building. And then there's special cable glands as well. If you want very cheap and easy shade analysis, you can go to Google Project Sunroof, and they will show you the light images of the house. And basically, these light images will show you the impacts of trees so that you can say, okay, well, the south side of the house really is not that great for solar because of that tree. And so these shade analysis are really good for kind of looking at, do my nearby trees actually have shading impacts on my roof surface or not, which can be something that's a little bit difficult to judge remotely or even from the ground on site. But the basic principle of our design process is we pull up the building, we map out the roof, we determine. So here we're doing a trick where you can do something similar with Google Earth. You can map out the roof with Google Earth. Here we're determining tree height from Google Earth by measuring the shadow and then determining the date that the picture was taken in. And if we have the length of the shadow, the other thing we get with Google Earth is the bearing of the shadow. So that shadow is pointed at 160 degrees, 20 degrees off of south. And so because we have the bearing of the shadow and the date of the picture and the location of the picture and the length of the shadow, we can use trigonometry to determine the height of the tree. So there's a, a chart called a sun angle azimuth chart. The Navy makes a really good one. So you can go to the Navy sun angle azimuth chart, enter in your location of your Google Earth photo, put in the date of the Google Earth photo, and it'll tell you all the locations of the sun at that date. And so if the heading of my shadow was 160 degrees, I now know that that photo was taken at 10:30 when the sun was 27 degrees up in the sky. And if the sun is 27 degrees up in the sky and the shadow is so long, you can use trigonometry to determine the tree height. So a lot of this solar design stuff you can figure out from the comfort of your own desk. And if you really want to, you can figure it out without using commercial software. It's just that commercial software is going to make it a lot easier on you. And so some other things you want to pick up in the site evaluation is the location of the electrical service, where it enters the property, how it enters the property, what kind of conduit it's in, what's the size of that conduit, taking a picture of the service panel, identifying the size of the main breaker, seeing if there's any breaker slots available, what does the control room look like. All of that is involved in a remote site evaluation. Once you do your array layout, you put it into the racking design software. I think that's kind of a repeat. Here's an engineering service online called Solar Roof Check. I don't want to kind of give away his business, but this is revealing for other kinds of information that an engineer might be interested in. Is in addition to snow load and wind speed, the type of lag screw, how deep it's going into the wood, all of that has to do with the pull-out strength of the attachment points. And then on top of that, kind of the shape of the load-bearing walls. The roof height, the roof slope, the type of decking, whether it's in surface board or plywood, or if you're just going into wood purlins. All of that stuff can play a role in your design process, particularly if the rooftop is commercial or not a standard kind of pine rafter roof. And so building code has load combination calculations to check that will say, okay, what's the dead load of the roof? What's the dead load of the roof in high wind? What's the dead load of the roof in heavy snow? What's the dynamic load and live load of the roof in high wind with heavy snow? And all of this structural information, the rafters, the lag screw size, goes into determining if the building can take the solar array or not. In most residential projects, the installers just really err on the side of being conservative with their attachment points and design work rather than going through this stuff. a standard solar array is going to add about 3 pounds a square foot of dead weight onto the rooftop. So, computer assisted solar design can exceed the capabilities of a human. There's a lot of design software out there to help you with the design. Most of the design software does not have battery components built into it. That's a shortcoming. Batteries with solar, they used to be standard back in the 70s and 80s and 90s and early 2000s. Nowadays, most solar arrays do not have batteries. They're aimed at lowering the electric bill, and one of the ways to do that was get rid of expensive batteries. Now we're coming back full circuit. Batteries, while still very expensive, are more affordable than ever. Some of the solar policy is getting unfriendly, and batteries are now the solution for that. And so I'm finding where the real need for hand design is how to design battery systems. The software is just not, the design software for battery systems is not just there yet. It's no coincidence that I've been asked to inspect some design plans, and I'm starting to see some errors on undersized conductors coming out of the battery bank because installers are not used to doing a full proper design anymore. All right, so we'll save the last few minutes of our program for running through some of the software pictures, but let's skip over this for now so that we have enough time to get through all of our lecture content. So how do you do battery bank sizing? Well, in off-grid design, you have to be very aware of the peak load of the home, because instead of designing the inverter to fit the solar array, you have to make, the solar array may only have this much power. Off grid design, you have to power the whole house and not just the solar array. There's also, even for grid tied homes, this concept of well, maybe the solar array is producing in the middle of the day and I'm using my energy at other times, and then I have to value the surplus that's being bought back from the utility. I have to know the rate that that's being bought at, and then maybe I have a variable rate structure where I have a higher rate in the morning or evening or throughout the entire day versus off peak. And so, how do I start kind of untangling the economic calculation for that? We'll show you some software for it. Basically, I used to model it in Excel myself, but then the software became good enough, better than what I could do, so I start using software for it. Let's dispel a couple of notions about batteries real quick before we get into that. Let's just look at the cost of the Tesla Powerwall 2. Popular battery product. The material cost of the Powerwall 2 is $6,600. So let's just assume that half of this money was for the inverter component and the other half of this money was for the battery component. So if we took $3,300 and we divided by our Tesla Powerwall 2 warranty, which is for 40,000 kilowatt hours, the cost of the actual batteries inside that Tesla Powerwall 2, if you look at their warranty, their cost divided by their warranty, being very generous to Tesla, the cost of the battery is 9 cents a kilowatt hour. And what's interesting about that is if I have a peak versus an off-peak rate, and that difference is less than 9 cents a kilowatt hour, if I store the peak energy during peak times, and if I store the energy during off-peak times and I discharge it during peak times, I might be saving 5 or 6 cents off my electric bill, but it's costing me 9 cents to run the batteries. And so using batteries to fix the inflow versus outflow issues of a residential electric bill, it doesn't necessarily result in more economic benefit to the customer. Now, sometimes the customer won't care. If they bought the batteries, they want to use the batteries, even if it doesn't make economic sense to do so. They want that low electric bill. Okay, let's talk about the design process with the batteries. Well, and we have a class coming up with PDH Pro for off-grid design. And the main difference between grid tied and off grid is in grid tied, you're kind of sizing up annual energy usage and coming up with a solar array to produce annually. And off grid, you're looking at the worst months of the year. You're looking at wintertime and you're looking at summertime, and you're sizing the array to produce all the energy you can during those months. So an off-grid solar array is going to be substantially larger than a grid-tied solar array. And we talked about how you can use PV watts to determine how many days in a row you can go without sunlight. Also, you can use PV watts to determine the difference between, a day where it's lightly overcast versus a day where it's very overcast. So that's kind of interesting too, that there's different kinds of overcast days. And so here we are charting our PV watts data for every single day of the year and then visually inspecting it to conclude, okay, well, here along this time frame, there's a period where we go 4 days without sun. So we get more into detail in this in our off-grid design classes. But the short of it is, if you have your electric bill, you can divide that into months of the. It's already divided into months. You can divide that into days, and you can divide that into hours by just making some assumptions about the home load profile. And those assumptions aren't going to be very good assumptions, and so you have to be conservative in your model when you're modeling it this way. But basically, we take our production and we take our consumption and we subtract the two and we establish an upper limit that the battery can't charge beyond, and we put in our array size and our battery size, and we start to look at what is the minimum size of a battery bank that we need to not run out of electricity. We just don't have time to go into all of the details, but the fact is, almost every off-grid home is going to have a backup generator to overcome deficiencies in power generation. You're not going to use the generator all the time, but you're going to use it. And so when I'm doing off-grid design, I'm looking at my model and I'm saying, okay, well, if I add a pallet of solar panels, can I significantly reduce my battery bank size? If I subtract a pallet of panels, my battery bank size then substantially increases. This is a typo. There should be 14 right here. And so I just do a whole bunch of different simulations to determine what my optimal array size is for my off-grid system in terms of the right combination of generators and batteries. In interest of time, we're going to skip over this slide. Now, this stuff really doesn't matter too much. Whether or not you're using one inverter for the whole system or separating out the battery inverter from the solar inverter, these are technical discussions that installers really like to consider. But the short of it is, it's flexible. You can do whatever you want. And generally, I'd recommend having the battery be on a separate inverter from the solar array, because there's not much difference between the two in cost effectiveness. And anyway, that's all I'm going to say about that. Commercial batteries are different than residential batteries. Commercial customers are billed based off the very top of this power level. So residential customers are billed for the area underneath this curb. Commercial customers, only half of their bill comes from that. So commercial customers are billed 50% less for their energy than what residential customers are on. And because a solar array comes in and reduces your energy, if that energy is worth half to a commercial customer than a residential, that's why commercial solar stinks. Is because the solar array is only producing half of what it would do. It's the same production, it's half the value for a commercial array versus a residential array. So even though commercial can get those lower prices, they don't have the right billing structure to take advantage of solar. At least that's been true for the last 10 years. Now you can have a battery and you design the system to just deploy peak deployment. So you'll charge the battery with your solar array during the day, and then you'll discharge it during peak times for maximum savings. And so here's a commercial software called Energy Toolbase that models this so that you don't have to in Excel. And basically, it takes a good computer to crunch every single interval for every single day and to run a bunch of simulations to determine your optimal size. But the way these systems work is, they are tied into your home meter and turn on and just shave, the peaks off of it. And we have a commercial battery sizing class scheduled with PDH Pro coming up where we get more into the nuance of that too. But the short of it is the commercial battery market, the commercial solar market right now is the smallest market segment. But because of what batteries are doing to demand charges for commercial rate structures, it is actually producing the best and quickest payback in the industry. So if you're in a market that has low solar production but high solar value, you might be able to get a 9-year payback for a cheap residential solar array with net metering. In that same market, you can get a less than 9-year payback for a commercial battery system. If you are in a market that has good solar production but really bad energy rates and your payback is up towards 13 years or more, you might not have any residential solar market, but you could still get a good commercial payback because of the way commercial bills are divided between energy rates and demand charges. And so here's a software called Energy Toolbase that focuses on economic modeling of commercial solar batteries, and it produces cash flow diagrams to a level of detail that would make your CFO smile. Installers are not very good at economic modeling. They confuse things like pre-tax analysis versus post-tax analysis, and the tax credits and depreciation incentives throw in additional considerations. But that is why you want a computer software to do this kind of financial modeling rather than just take the installer's word for it. So here's some screenshots of Energy Toolbase. And so what's interesting here is here Energy Toolbase is modeling solar on a sunny day. Normally the building's peak demand occurs in the middle of the day, but now because of the solar array, they see a demand reduction. The problem is on a partly cloudy day. On a partly cloudy day, you still have high demand, but if the solar array turns off, then the building's demand spikes right back up to where it would be until the cloud passes back over the roof and the array turns back on again. And so what Without a battery, you cannot guarantee demand savings with solar. But all you need to do is add a very small battery to the equation to kind of play free safety. And at that point, that unlocks the demand savings. So the problem with commercial solar in years past is that it's produced demand electricity at demand times, but the customer has never, on a demand rate structure, has never been able to result in actual savings. But now with lithium ion batteries, that whole equation is doing a somersault, and all of a sudden you can do above retail generation with a commercial solar battery. And because the value of that electricity is the most expensive electricity on site, you can install a more expensive battery system and still get a better payback. Last but not least, I want to show you an example of my own electric co-op, Coast Electric Power Association on the Gulf Coast of Mississippi. This is a co-op that has a terrible solar buyback program. They give you nothing for it. In fact, they charge you money. It was a horrible solar program, and years past, I've just railed against how awful their and it's a monopoly. It's a cooperative. You have no choice but to buy power from them, and they give you a very bad consumer solar policy. Okay. They also have a time of use rate structure, a higher rate at certain times of day and a lower rate at other times of day. And their time of use rate structure says, okay, you normally get billed 9 cents a kilowatt hour. We're going to give you a time of rate where you're being billed 4 times as much during peak times, 3 hours in the summer, 2 hours in the winter, and then all other times we're going to bill you half as much. So say, okay, well, if my demand is flat, theoretically at peak times you should have higher than above demand. But if I can go and manage that, then if for 3 hours a day during the week, that's about 10% of the year. For 10% of the year, my bill goes up by 400%. For the remaining 90% of the year, my bill goes down by 50%. And if all else is equal and my demand is stable throughout those periods, I'm going to save 5% on my electric bill by doing nothing but switching onto this peak variable rate. And then what I would do with Energy Toolbase is go in and model not a solar array that covers my entire rooftop and targets 100% of my electric bill. And this is just screenshots of Energy Toolbase. They have most electric rate structures, but if they don't have your electric rate structure inside, these are the screenshots of modeling that time of use rate structure within the software. So often these peak rates versus off-peak rates are during the week versus weekends. Sometimes they exclude holidays. So here we're in the software and we have different inputs for solar, for batteries and storage, kind of creating our proposal. We're uploading our building's electrical data. So this is where you can put your commercial 15-minute by 15-minute interval data. If you don't have that, then they're making a guess, just like what we saw with Aurora Solar earlier, based on your actual electric bill and what appliances you have in the house. They'll just guess for you what your load profile looks like. And so here we're importing our electric bills or trying to grab our data directly from the utility. Some utilities make this data more readily accessible, others don't. And then it's modeling our peak versus our off-peak rate and doing an economic analysis of that. in the interest of time, I'm just going to keep moving forward. So here it's modeling the fact that I don't have any net metering at all, and my energy buyback rate is only 5 cents. And what's interesting is if with just a little bit of energy management, um, I can save. If my normal electric bill is $1,900, if I can just get my demand to be flat during those times, I could save a few $100. And if I could really kind of eliminate my peak rate during that time, I could lower my electric bill by $500. So I could, or $500 to $600. So by reducing 10% of my on-site energy use, I could lower my bill by 30%. So instead of net metering, that's a 1-to-1 ratio. If I have the right time of use or peak versus off-peak rate structure, I could have a 1-to-3 ratio without selling back a dime of electricity by just preventing my home from using electricity during peak times. And so here I can put in my PV system. Helioscope, a solar design software, can input directly into it. But we're also seeing this is where the PV watts data is coming back into play from earlier today. You put in your array size. It's connecting to the PV watts weather station. You put in your project budget. Then there's an energy storage component. You put in your energy storage size and cost, and then you get some energy optimization analytics that come out of it. What's interesting about kind of a solar peaker, where you're not trying to do the entire building, but just a small section of the building's peak energy, is that the larger the system gets, the more you approach having, just a 1-to-1 ratio, or even worse, depending on your buyback rate. If you have a very spiky peak load, shoveling, level, your savings are linear, but your system is having to work harder and harder and harder the more of that peak you're trying to level all the way down to zero. And so by just staying at the top of the peak, you can have, it's weird, but it's the opposite of economies of scale. Smaller systems can be more cost effective than larger systems. And Energy Toolbase will kind of start to kind of show you, hey, once you start getting past about 8 kilowatts of 8 kilowatt hours of system capacity, you're past the storage that you need to just store 10% and deploy it during peak times. And anything more than that, you're approaching whole house backup, and that's going to be less cost effective. And so the advantage of the software is like, so you can get in and you can see, every single day and figure out what's going on. Okay, so my solar array is turning on and my batteries are charging back up, and my solar array is turning on and my battery's charging back up. But now my solar array is not turning on and I'm having to use a little bit of grid power to keep my battery charged. That type of stuff is modelable now in the software that's available on the market. Different modes of operation. Again, not trying to get into the software training side, but do you want to just go after peak demand savings, or do you have a variable rate structure for your energy component? Return on investment, levelized cost of energy, payback periods, net present value, all reduced down to formula. And so here in this model, if I wanted to optimize my system for my utility rate structure, it turns out that if I do a 10 kilowatt battery on a 5 kilowatt inverter, it has a higher generation rate than if I do a system that's twice as large and only 50% more expensive. So sometimes the small, highest unit price system, when it comes to peak rate optimization, the smaller, more expensive system can outperform the larger system that has an economies of scale discount. It's kind of fascinating. So in my case, with my rate structure, now I'm designing a system just to completely eliminate my load for 2.5 hours a day, and that's it. I'm not designing a system to offset my entire house, just that one little load. And while we don't have time to talk about it today, the latest and greatest generation of products, and I'd say one inverter company that's ahead of the game at the residential level for it is called Solarc, and at the commercial level, Delta. These two companies in particular are way further ahead in their control systems for dispatching this energy in an automated fashion than the other guys. Um, let's see. These are just some graphs. We don't have too much more time to talk about it. Just some more energy tool based charts. Let me go ahead and put in so we don't run into a rush at the end. I'm going to put in my email address, john at community.solar, or you can use my Gmail, either one. If you send me an email after class, I'll give you a copy of the course recording and show you where you can find my course handouts so that you can keep this information afterwards. So just shoot me an email after class for that. There's one more topic. So we're just talking about some reports for this. Nothing real important here. Generally speaking, they Energy Toolbase provides some reports, but generally the more cost-effective battery system is the one that more deeply cycles and utilizes the battery more frequently. If you have a battery that is not being used to its fullest extent on a regular basis, then that battery might be oversized. You might have too much storage capacity versus something that is a little bit more cost effective and because it's being used. In the interest of time, the last thing I want to kind of go over is there's also a way to take this demand energy and remove it without using solar or batteries, and that's through load control. So smart home technology now, really I say smart home, but you can use this stuff on businesses as well, will put a meter around your home that will provide your real-time electric use as an input. And residential homes, their load profiles do not look like nice little smooth curves that you see. They're very, very up and down and spiky. But now you can have smart thermostats to talk to other devices, smart plugs that talk to other devices, and a smart, meter that talks to other devices. In an off-grid system or in a system where you can't sell back to the grid, it results in stranded electricity that you don't get any value for. So how do you put more of that electricity to use? Well, you could store it in a battery, but then the battery gets full and you still have stranded electricity. If you had a freezer on a smart plug that turned on and off as a function of electric load, that freezer can coast for a few hours without any loss of value to the food. And so if you have a time of use rate structure that's for 3 hours a day, or a building peak demand structure that's for a half an hour or 1 hour, could you turn devices off and then turn them back on again to do on-site demand management cheaper than solar or batteries? Solar and batteries can do this, but they're very costly. One thing you might do is use two freezers and then fill the half of the freezer up with ice and just give it use water as your battery effectively. And even though this total system might use more electricity than just having one freezer, that's really not the point. The point is, by doing load leveling, you can use the freezers during times of cheap electricity and then take them offline during times of expensive electricity, so you can actually use more electricity than you currently are, but still have a lower electric bill. And so, whereas a solar array will only tell you the monitoring information of the solar array itself, and sometimes that monitoring can be very good, you need to add a monitor on the building consumption meter in order to enable kind of advanced smart control for energy management. We actually have a class that's 2 hours for this called Smart Home Load Control that's coming up on PDH Pro's schedule. But basically, these consumption meters click around the power lines that come into the building that you would do, say, a supply side connection on. And then in any smart software platform, I use an open source one called Home Assistant, but this data starts getting communicated so that you can program with it. And so I have an off-grid customer where as soon as their electric load spikes, we turn off their water heaters and turn them back on again when the load drops down. And that takes off peak load, and that allows them to operate on a smaller system. It's useful for residential off-grid. It's useful for commercial demand management as well. Furthermore, you can take your electric water heaters and say, okay, well, I want you to not turn on at 4 a.m. I want you to turn on at 7 a.m. when the solar array is turning on, so that you're running off of the solar power and not off of grid power. So smart controls can be used to kind of fine tune the system. One of the things about residential battery backup systems is that they are not powerful enough to run the whole house. So you have to choose between your lights, your refrigeration, and your garage door versus your air conditioning. I live down south. The last thing I want you to take is my air conditioning. I'll lose $200 of food in the store. I don't want to be hot. Well, most battery backup solar inverter manufacturers say you can't use air conditioning because that takes all the power we can give in our small battery system. But with smart home load control, you can actually start running more appliances off the same inverter and battery bank by giving them priorities on what to power, making sure not everything turns on and off at the same time. So that's kind of a more interesting, nuanced application. But given that we only have a few more minutes left in class, if you want more info on this, send me an email. I'll give you the handout and you can read it in your own time. But there's a lot of ways that smart load control can complement an existing on-site energy system to get more value out of it, as well as function as a standalone solution. So for example, if you put your if you put your, we do an example of a hotel that has a whole bunch of air conditioners. And if we can just turn these air conditioners off at peak time and just run them harder during the time leading up to that, the savings comes from reducing our peak. The energy charge is going to be the same either way, regardless of what time of day these units run. We're trying to get them to run during off-peak times and just not all turn on at the same time for those 15 minutes. And so if you have a $10 per kilowatt demand charge, 1 kilowatt of reduction will save you $10. It doesn't matter if that reduction period is for 1 hour or 4 hours or 10 hours. 1 kilowatt of reduction at $10 a kilowatt will save you $10 for that month. And so if your peak demand time is only for 15 minutes, then you run the system for 15 minutes and you could save $40 per kilowatt hour. A 1 kilowatt system running for 15 minutes out of the hour can save you $10, and the savings for 1 kilowatt hour for 15 minutes might only be a couple of bucks. And so demand management is really where it's at, because your savings can be much larger than the cost. And so if you put these air conditioners on smart relays, and every smart relay, the total project cost is $200 per air conditioner unit, you can get your money back in under 2 years, compared to solar or batteries where it's more like a 13-year payback, 10 to 13-year payback. Um, so that's just kind of interesting and something to look into. Uh, the smart home load control class, we go through the setup process of an open source energy controller. So that we're teaching that in a couple of weeks, and that should be an interesting one where we get into all of this detail. Okay, so we didn't get into as many design examples as I wanted to, and so I'm going to show you a resource you can go to where you can see some actual course videos. So I'm going to put it into the chat box right here. So this is where you can go to get the text of this program, and then basically when you start with halfway through the program, we just did the lecture slides today, but in the videos that are on that web link that I sent, we get into showing some of the commercial design examples. So just real quickly, we're just going to take 2 or 3 minutes to go through the highlights. This software is called Scallion, and it integrates with Google SketchUp. And so it actually does a 3D shade analysis based on your three-dimensional drawing that's already built into SketchUp. And so if you're already using commercial SketchUp, then Scallion is a really good one for just inserting inserting solar panels on top of your existing SketchUp models. One of the softwares that I think is probably the best of show is PV Complete. Now, PV Complete is very difficult to use, but it is based in AutoCAD, and it will do commercial electrical diagrams. So it does kind of overhead modeling, but the real benefit of PV Complete is that whereas Solar Design Tool only results in one line diagrams for small projects, PV Complete scales up so that you're doing one line diagrams of commercial and utility scale projects, all based on templates. It's just you have to be pretty familiar with AutoCAD for this software to not be clunky. But then it puts it all into project reports, material lists, makes it easy for you to export it into one-line diagrams. Um, this video number 3 shows off aurora and helioscope. So we have the recorded video lecture, but then I want to show you. First, we're going to show you aurora, and I swear we're ending this program in a minute or two. Um, So that resolution's pretty bad. You might have to go to the website to do it. But this is called LiDAR data, LIDAR data. And so this is the advantage that using some commercial 3D modeling software does, is that, based on the elevation of nearby trees, you can, easily create a 3D model within their software interface, and then model nearby trees based off this elevation data, and that's pretty useful. So without getting into the rest of it, there's a kind of a walkthrough that shows how they go kind of from start to finish, clicking on the rooftop, and then within a matter of a few minutes, they're able to pop the video, the 3D building out of the map based off the rooftop sketch, and then go into some kind of advanced featuring that'll let you do the same process with new construction. Um, Once the rooftop is mapped out, they're just adding solar panels on into it. This is Helioscope. They're Aurora's main competitor, and they do kind of the same thing. Um, I would say Helioscope is less feature rich, and it's also less expensive. Helioscope is more focused on being the array layout and shade analysis, whereas Aurora is trying to be more of a one-stop shop software that does a little bit more stuff at a little bit higher of a price point. So both Helioscope and Aurora are great for residential shade modeling, and then they both also do commercial shade modeling as well. Um, Although with commercial projects, you generally don't have nearby trees around, so trigonometry and common sense is really all you need. But here's an example where they're modeling a commercial array layout with setbacks for a commercial air conditioner unit, and then modeling the shade that it casts, and that can be useful information when doing a commercial job. So. Um, at any rate, we are out of time. So, 4 hours. I hope you learned a lot of information about solar design. I'd say there's one more software that we didn't get into called Solograph, which is more of a sales software. So it's not as important as these other design softwares. But I guess the what I wanted to say is Solograph, um, they claim to be doing shade analysis. They have a very similar process to Google Project Sunroof. Again, all of this design stuff is the same. You're tracing out the rooftop, it's filling it in with solar panels. And so what I would be careful with Solargraph, because they claim, they do permit documents and they do other things, but their shade analysis is using Google Project Sunroof data. And so the Google Project Sunroof data is good. Like, you can see this west facing roof surface is not good for solar because of these trees, but they're not doing a full 3-dimensional shade model. Only Aurora and Helioscope and then SketchUp with Skeleon are the only softwares that I have found that actually do module level 3D modeling. And so that's something you end up having to pay for in the industry. So, both Aurora and Helioscope do free trials. All of these software companies do free trials. the next step on your solar design journey is to sign up for some free trials of solar software and try and run through some simulations for that. So, with that, we are out of time. Thank you for sticking around. I'm going to pass it back to Jerry. Hey, Jerry, are you there? Yeah, Jerry, I can't hear you, but I think it might be just me. I'm not sure. Yeah, no, it's just me. I see your feed coming